Okay. Um, Hello, can you hear me? Okay. Yes. Hello, everyone. My name is Yanwei Fu from Fudan University. Welcome to our CPR 2022 tutorial about learning sparsity in neural network and robust static analysis. I'm the hoster. So this tutorial is collaborated with with Mr. Yikai Wang, Professor Yuan Yao, Dr. Xinwei Sun, and Professor Wu Taoyin. I share the screen, and you can see this is the basic schedule of our talk. And we spend 10 minutes to give the brief overview of talk, which is right now. Um, First, I will give a talk about, give an introduction overview of our tutorial. Then Yikai, who is my PhD, will spend 20 minutes talk about sparsity learning in noisy data detection. And Professor Yuan Yao will talk about inverse scale space method for sparse learning and statistical properties. And then we have 50 minutes break. After that, Dr. Xinwei Sun will give a talk about spatial learning in medical imaging. And finally, Professor Wu Taoyin will talk about learning to optimize algorithm unrolling. Basically, this tutorial is a we'll talk about learning sparsity, and we will give some algorithm statistical perspective, algorithm perspective, and also some application in computer vision and medical images. So, well, very welcome to this tutorial. Uh, I'll give some further details why we're using this title, learning sparsity in neural network and robust statistical analysis. Basically, we want to divide it into two parts. One part is learning sparsity in labels and data. One part is learning sparsity in deeper model. So we also have a website, which is this URL. Maybe you can check the detail of our tutorial. We will put all the slides and talk online, and also some other material to support our tutorial. Let me share this screen about. So this is a. This is the web page of our tutorial website. Okay. So this is the overview of our tutorial, and let me start. Let me start the first talk. So I briefly introduce myself since I'm the hoster. My name is Yanwei Fu from Fudan School of Data Science, Fudan University. Currently, I'm a tenure track professor. So I got my PhD from Queen Mary University of London in 2014 and work as postdoc at Distant Research Pittsburgh from 2015 to 2016. And also got some awarded as a professor of Eastern Scholar and 1,000 young talents in China. I published more than 100 journal and conference paper, including 10 PAMI paper. My research is about one-shot learning for image and videos and learning-based 3D construction for modeling object bodies and robotic grasping and image synthesis. Okay, thanks. Let me start my. Okay. So can I assume I'm sharing the screen, right? can you show can you?
Yes, we can.
Yeah. Okay. Great. Thank you. Okay. So let me start. Maybe I can wait another 2 minutes. Let's start from 9:14. Yeah. Basically, Xinwei Sun from Xinwei from also is my colleague from Fudan University, and Yuan Yao from Professor Yuan Yao from Hong Kong University of Science and Technology, and Professor Wu Taoying was a UCLA professor and now in Damo Academic Alibaba. So if any if you have any problem, welcome to email us, and we have some the email address in the tutorial web page. Okay, let me wait for one more minute. Okay, probably I can start. So, welcome again. Hi, everybody. Glad to be here. My name is Yiwen Fu from Fudan University. So, let's start my tutorial. And this is the first part of our tutorial. I'll start from the motivation. So, let's give some overview. Probably some senior researcher know that 10 years ago, there's a very good tutorial, ECCV tutorial about sparse and low rank modeling given by Professor Yima, Professor Alan Young, and Professor John Wright. So it's about it's also about sparsity, low rank, basically sparse representation. Compared with that tutorial, our CPR tutorial is more focused on learning sparsity in labels and data, which is good for robust statistical analysis. And also learning sparsity in deep model, which could produce compressive neural network. Oh, sorry. Maybe I can open the live script. Yeah, it's enabled. Open the live script. Yeah. So our tutorial compared with that tutorial, our tutorial is more focused on deep learning sparsity in label and data, which is good for robust statistical analysis, and also learning sparsity in deep model, which could produce compressive neural network. So on the right figure, we give the schedule of our talk, and my senior PhD Yikai will give some more detail about my talk. Okay. So let's briefly review the ECCV tutorial about sparse and low rank modeling. Particularly, the sparse recoverable data focus on the unmanned linear system, while the observation is much less than the unknown parameter, and the target is to extract compact knowledge from massive data. For example, in image compression, the input image can be decomposed by a small elements of DCT basis of be learned of as a learned dictionary. In recognition, the image can be represented with a combination of a training dictionary. And though this idea this simple sparse recovery of vector can be generalized to many other types of low-dimensional structure. For example, when we want to recover many correlated vector, that is a low-rank matrix, and we can formulate as a robust PCA problem. We can recover the phase under varying illumination of recover the background images from foreground motions. So to solve this robust recovery problem, we aim to minimize the number of non-zero parameters of sparse vector under the linear constraint. However, this problem is known to be NP-hard and are hard to solve in general. Instead, when we find some convex alternative to this problem, a popular way would be replace the L0 norm with L1 norm. And when we further replace the square loss of the constraint to the Huber loss, which is very famous in statistics. So, like in the overview of our two parts, first is about sparse learning in date and label. Here, rather than recovering the sparse feature from data, we will consider the linear system with noisy data and label. Particularly, the label and the observation are noisy. So now we have a linear system with noisy label and data. And we will introduce works of recovering sparse noisy data label for robust statistics analysis. Here we have the equation Y is the noisy one-hot label, X is deep learning feature with coefficient. So we want to identify which Y is noisy. This is our the red font recurring sparse noisy data label, which we are focused on this part. It's different from the sparse learning sparse representation or sparse feature from data in previous tutorial. And we give the key formulation here. We introduce a sparse indicator gamma here. You can see the gamma. We call it a shifted linear system. Here, you can see that the gamma is a predict residue of the corresponding data. So if we can consider this case, we assume Y is noisy, one hot label, X is a deep learning feature with coefficient. So for clean data, gamma does not need to correct the prediction. That means we don't need the residue, the predicted residue, and this will lead gamma will be zero. We call it a zero shifted prediction. But for noisy data, the observed label is inconsistent with the Oracle linear model, and the gamma should be biased towards the prediction of the linear system to the cropped noise label. So here we for the noisy one hot label here the gamma should have some value. It should be zero. And this makes different. For clean data, we want the gamma to be zero, and for noisy data, the gamma should not be zero. And this is the shifted linear system. So by using this system, we can do the sparse learning for noisy data and labels. If you have any question, please list it in the chat box. And we compare and list some application that using this formulation. For example, in robust regression of classification, we can using this formulation. Basically here, beta, we want to compute the beta. We give some example. This is a toy example, and the blue point indicate inner data, and the red point indicate the outlier data. And basically, this is the regression path we solve this linear system. We solve the objective derived from the linear system. And in statistical robust ranking, this formulation is used to solve the gamma and beta iteratively to progressively find the outlier and learn a ranking algorithm from noisy data. For example, this is a toy example, and the green line indicates the green edge indicates the inline voting, and the red edge means the outlier voting. And in face recognition, this formulation is transferred into a new standard linear system to recover the face under varying lighting of corruption of occlusion. And we'll give some details about this application in the next part of our talk, my talk. So before going into the detail, I'd like to give some understanding about gamma in statistics. So basically, the gamma is the residue predicted error, which is a naive method to identify noisy data from the dataset. We can write the gamma as this equation, right? However, in general, this raw residue fail to detect outlier at leveraging point, as shown in the left figure. And a better way is using the leave one out externally studentized residue to test whether the predicted residue is a large value based on the other observation, right? This is basically equivalent to test whether the gamma is zero in this equation. However, this can only be used for only single outlier. When there are multiple outliers, there are phenomena we called masking and swapping. So masking means that multiple outliers will mask each other or help each other, and making all the outliers being undetected. Swapping means that multiple outliers may lead to large T residue value for clean data. In other words, swapping means that the algorithm will make the clean data as the outlier. So here, we'll consider the whole indicator matrix for all training data in the matrix formulation. Okay, I'll further give the overview of sparse learning in deep models. We want to learn effective sparse network structure from with good performance. This is the left side figure. For example, if compared with the densely trained model, the specified model will put a lot of filters and parameters at zero without sacrifice the generalization ability. This is why we want to learn in sparsity in neural network. For example, in this example, the specified model, this particular convolution layer, and for this filter, we can simply drop this filter and only using this filter, and performance keeps the same. From a general perspective, we want to balance the model property of over-parameterization and compressive sparsity. So, despite the benefits of over-parameterization, a huge amount of parameter makes deep network too heavy in daily life application. On the other hand, training neural network without over-parameterization faces many practical problems. For example, being trapped in local optimum. So to sum up, in general, the success of DNN deep neural network relies on a huge number of parameters, while it hinders the deployment of unlimited resources machine. And the compressive network is desirable with less memory and completion cost. So this task is potentially very related to recent well-known foundation model, right? We highlight the dilemma of foundation model. A foundation model can centralize the information from all the data from various modalities like text, image, space, structured data, or 3D signal. And this foundation model can be applied to a wide range of downstreaming tasks. So to train the foundation model, I summarize a 4B, which means we need big data, right? We need a big machine, and we train big model. And that means we should have big money, right? Big fund. Realistically, it's only possible for very big company of agency. On the other hand, we want to use a foundation model for various tasks like question answering, sentiment analysis, image captioning, object recognition. But in adapting foundation model to specify downstream task, we need to prune the model. We need to prune irrelevant parameter and reduce model size. This can benefit deploying the model to specify the target task with limited resource machines. So essentially, we want to compress or specify the foundation model on this task, like robotics, like edge devices, self-driving cars. And there are a lot of great work recently on foundation model in computer vision and machine learning communities. It is actually quite topical recently. We summarize some recent foundation model, including CLIP, Alan, Abe, Florence, Nova, Intern, Gopher, Glevel, and Opt. So to some degree, it urges us to study learning sparsity in deep foundation models. Okay, let's give some detail on the first part, learning sparsity in data and label. We will give some application. The first one, we start from future learning task. So I assume we are very familiar. I assume the audience are very familiar with future learning. Basically, in future learning, we only have access to few label data to train the model. Furthermore, in industry, it is also cheap to collect massive, noisy, unlabeled data. So we can think the classic self-taught learning pipeline. So in the self-taught learning, we first train the future model with labeled image label pairs, and then we infer the pseudo labels for unlabeled data. We can further boost the future model with this pseudo labels image. Here, the core problem is that how to ensure the training with the pseudo label image is trustworthy, that the retraining will not damage the performance of original future learning model. That is very hard to do, as the pseudo labels are very noisy, and the future learning model is not trustable. So we'll show how to identify the credible ones from noisy pseudo-label set. We will model the features and one-hot pseudo-labels by our shifted linear system with noisy indicator. We solve this system and simplify to a standard linear regression of noisy indicator. Here, we're using the F norm, which corresponding to the penalty to the epsilon, and R is the term for the gamma. And to solve this linear regression model, it is important to select the prop lambda here, right? So let me think. The classic methods for selecting lambda would be heuristic rules, cross-validation, data adaptive technique of AIC-BIC. However, popular approaches are not applicable in our case. Obviously, each element of gamma is directly connecting to one image pseudo-label path. For example, in k-fold cross-validation, we will have some withheld data, and this data shall also have some corresponding gamma, which are unfortunately unable to be optimized in this case. That's why cross-validation cannot work here. And we will generate a solution path or regression path to better identify the noisy data, and Yikai will give some details in next talk. We further give the application of training deep network with noisy label. So we propose to interactively do the feature learning and sample selection in the training time. The key difference from standard or vanilla deep learning training is that the training data is very noisy. So in the first stage, the network is trained with cross entropy to extract features and classify label. As they are noisy label, the network is not well trained. To solve this problem, we need to identify noisy data and remove them from the training set. So here, we assume a linear relationship between the feature and the one-hot labels. Interestingly, this linear assumption in general hold in many dataset, and we think it's reasonable because the deep learning, fundamentally deep learning is a representation learning, which means give some images of sentence, and we're learning some good features, and this feature should be the very non-linear extraction from the image of data, right? And the backbone should be highly non-convex. And for the classification layer, and we can generally safe. It's safe to assume it's a linear relationship between the feature extracted and the final labels. And if we can check some recent works and a lot of works from Facebook and Google, they basically directly using the linear classifier in the final layer. And so those break this assumption, this linear abstraction will be identified as a noisy data. We solve this linear model with the sparse affinity on the noisy data indicator. And by using the solution path, we basically rank the data by the selecting time. And here, this is the solution path. Here, the axis is corresponding to the value of lambda, and y-axis is corresponding to the magnitude of gamma. If we think that the lambda changing from infinite to minus infinite, and the value of gamma will be changed, follow the changing of lambda, right? This is the solution path, and This is and the way here the blue lines indicates the clean data, and the red lines indicates the noisy data. And this is the end of the second stage, and means the sample selection. And we return to the feature learning stage and repeat these two stages entirely until converge. To further make the linear system scalable to large data set, we first compute the class similarity matrix and divided the most dissimilar class into groups. So, and for each group, we select a small number of training data to construct small pieces of data, and then our algorithm will be running on each piece of data in parallel. Basically, this simplified our algorithm and make it scalable to large data set. Our shift linear system can also be used for cross-sourcing ranking task. Particularly, given two paired images, we can do the cross-sourcing and ask a lot of people to give the voting. Interesting, this task is very related to the task of named learning relative attributes in computer vision. For example, the man, the B in figure B is less smelling than figure A, but more smelling than figure C. And the figure E is less nature than figure D, but more nature than F. So basically, in relative attribute, for relative attributes means that we have some attribute. It's very hard to give 0, 1 labels, but we're using the relative comparison to help label the images of data. And in comparison, we call this task as the subject visual property. So for the cross-sourcing data, even using the paired comparison, this data will be very noisy due to many factors. For example, culture factor, and psychological factor, ambiguous comparison of lazy annotator. For example, I gave the figure here. Yao Ming has some special faces, and Asian people will think he's smiling, but in general, it's ambiguous. It's an ambiguous instance. Here, I'm using one toy example to show how we construct the learning sparsity for robust ranking. For the left figure, we do the age estimation. We collect some cross-sourcing path, which indicates by the direct edge. And the red edge means outlier voting, and the number here means how many people do the voting. So the model will learn on the left subfigure and will give the prediction of the age on the right two photos. For example, here, that this edge means that two persons think the person in this image is older than the person in this image. Obviously, this is outlier voting. And by using this cross-sourcing path, we construct direct graph. W and E. W means the node, and for each node, we can extract a feature. We indicate the phi. Phi I means the feature for image I, and phi G means the feature for image G. And we introduce the shifted linear system and using gamma Ig to indicate whether the bolting Yig is outlier or not. And furthermore, we can write the dataset into the matrix formulation. Here, the C is the instance matrix, and the phi is the feature for all nodes, is the feature matrix for all nodes, and beta basically is a coefficient. And basically, we still formalize as these objectives, and we using SVD decomposition on this C phi matrix, and we can simplify the gamma as this objective. So, interestingly, this leads to a precondition lasso problem. This is a precondition lasso, and to solve this objective, we basically still checking the regression path. Here we give a toy demo to visualize the solver. The blue point indicates the inline, and the red point indicates outline, and we basically using this precondition lasso formulation and check the regression path. And here the axis is still the lambda, and y-axis is the magnitude of gamma. Basically, following the regression path, the outlier variable will come first, which is the red line here, and the blue lines indicates the inline. So now I also talk about the learning sparsity in neural network. In general, we like the idea of over-parameterization. We like the over-parallel network, which have good expressive power. However, we do not like a million parameter, which are hard to be used in many real-world applications like robotics or self-driving car, right? Therefore, the compressive network without losing of performance is desirable. So to achieve this goal, researchers basically proposed two-stage approaches. First, fully train dense network, then find good sparse subnet. And there are a lot of common practice of old school techniques like network pruning, regression, knowledge stew, and recently proposed lottery ticket hypothesis. Unfortunately, without over-parameterization, compressive model, if directly trained by optimizer, such as SGD, may be trapped in local optimum. In contrast, we're thinking a one-stage approach without fully train a dense network. So let's briefly review previous work, regression and over-parameterization. Existing work leverage the regression, such as L1 regression, which enforces sparsity on neural network of L2, such as VCK. However, training with regression can decrease the capacity of network, leading the local optimum. A series of recent work have found the advantage of over-parameterization model in terms of optimization and generalization. So training over-parameter model can be viewed as a linear approximation to the network function, which makes it easy to find global optimum. In addition, the weight size dependence complexity as multiplied terms of Lipson's constraint are controlled, which can explain the better generalization it obtained. However, the over-parameterized model suffers from large inference time and memory cost. As for network pruning, pruning is actually one of the most straightforward and direct way of producing a light model. And network pruning can be roughly categorized as a weight of filter pruning by checking whether removing some structure parameters such as convolution layers. And the common practice of pruning would be first we first by learning connectivity by non-network training, and then prune the low-weight connection and retrain the network to learn the final weights for the remaining sparse connection. And we list some works. This example paper from Dr. Song Han from MIT. Actually, Dr. Song Han have a lot of work on this. Also, it's a quite related topic is quantization, which is useful for hardware acceleration. So our question here, can we do the sparsity in a unified algorithm? In the sense that we want to do the pruning in weight level, filter level, or even layer level. Can we do that? This is a question we can ask. Also, there are some other works of learning sparsity on transformer. This is like this work of pruning over-parallel structure with recurring. So this is a recurring model structure, which is very interesting and partly inspired our algorithm. And the knowledge dispute is also a well-known concept. In distillation, the knowledge is transferred from the teacher model to the student model by minimize a loss function, typically in which the target is a distribution of class property predicted by the teacher model. So this is a knowledge dispute. There are actually quite a lot of work on this topic. Another interesting hypothesis has been proposed recently, named lottery ticket hypothesis, which is defined as defining the winning tickets as the subnetworks which can obtain comparable result to dense ones if trained in isolation. This is a very famous idea, and I think this paper won the best paper award in iClear 2019. However, Pritz's work revents from initialization to find winning ticket subnet, which is very consuming. So we're thinking whether we can do it cheaper, right? For example, with only stopping, whether we can find some sparse subnet as winning tickets in lottery ticket hypothesis. This is actually inspired our work next. This is the key idea of our work. We propose optimizer named DESI-LBI, which is the abbreviation of deeply structured splitting linearized Bregman iteration. Here, basically for over-parallel network in space W, we basically lifting the parameter W to W gamma. And W is the training over-parallel model, and gamma introduced to learn structure sparsity in inverse scale space. We make a dynamic training algorithm named linearized Bregman iteration to train the dense over-pair model by W and structure sparsity by gamma simultaneously. And the structure sparsity learned by gamma provide a good candidate for subnet structure. Here, we expect that the more interpretable feature should be selected, while others do not in the inverse scale space. This is actually the nice property of inverse scale space, with the scales implying the selection time of feature. And Professor Yuan will give more details about the inverse scale space from a statistical perspective. And the larger the panty parameter induced the more sparsity of the model. For example, in image classification, the shape-based feature select first and the cost-found feature select later. And then we using LBI and get the compressor network WS. Here, basically, this is the operation of lifting to the by introducing universal scale space and using LBI to solve it, which combine together. We call it DES LBI. This is our advisor for this talk, and we'll give some mathematical and statistical introduction of LBI in the next talk. So why we come up with this idea? Basically, compare with the two-stage method. Our key insight is to lift the model parameter space by using inverse scale space. This is actually motivated by the PONET. Here, PONET is a method to analyze the PON data, and its aggregate in high dimension space preserve interesting property of the geometry. So it's also using the idea of lifting the 3D point to high space and then do the max polling, right? And we give some more intuitive insight of our method. Here, this is the illustration. In the original over-parameter space, the WS denotes the sparse parameter, which can be the winning tickets, and WSC is a complementary of the space WS. So due to the highly correlated WS and WC, it's hard to identify the good WS, basically. But if we think we lifting W and gamma into a high dimension space, the WS and WC can be quite likely be orthogonal, making WS easily to be identified. And we update the loss by using additional L2 regression here to keep the gamma and W close enough. All right, and our formulation is the differential inclusion of universal scale space, and we introduce Vt as the dual parameter of gamma t, and the Wt basically follow the gradient descendant with L2 regression. And equipped with this, the important feature of gamma t are easily first selected. Also, it enjoys a simple discretization version. We call it DES LBI. Basically, it's this formulation, and we divided this formulation into two parts. The first part is still the Wt. It's a gradient for W and the proximate mapping for gamma. Okay, let's give more detail about proximate mapping. The proximate mapping basically controls the sparsity, right? The proximum operator basically projects the dual element V into a prime element with sparsity enforcement. And the general form of gamma induce a Bregman distance. Here it degenerates to equidistance with 1 omega is L2 distance. And omega can be selected as group sparsity for filter and L1 sparsity for neuron in fully connected layer. And we this here. Interesting is enjoy a closed form solution. And also, our algorithm can be easily adapted to various forms, such as training with batch samples and with momentum and with decay. We present a theory in our paper shows that our optimizer is guaranteed the global convergence from any initialization. The depth API converts to a critical point. Our algorithm assumes the most defendable activation. ReLU could be approximated by soft class. If you want to check the detail, please refer our PAMI paper here, this paper. Okay, this is some discussion about proximal mapping. Actually, this is our PAMI paper is quite long about this theoretical and different version of this API optimizer. I've given a lot of experiments and in our paper. Here we select some. As an illustration, we show the DES API on main amnesty set. The left is our training path, and the right is a visualization of filters selected by gamma. And the x-axis is the training epochs, and the y-axis is the magnitude of filter. And we select 3 times 20, 40, 80 epoch. And we visualize the corresponding filter, and we show that our DES API make a very sparse filter, and in contrast, SED, a lot of filter are not sparse, right? And we also give example as we start our story starting from the winning ticket. So we can show that by using DES API, it's easy for us to identify the winning tickets. This is our result of the retraining subnet select by gamma. So first we train the DES API with early stopping. Actually, we can only train like 2, 4, 8, 16. We try different epochs with early stopping. And then we find extract the gamma as a subnetwork structure, and then we retrain the subnetwork, and we find the winning tickets. Here we show that on today's set, this is our result. It's much better than the baseline node. Means that our DES API can successfully identify the winning tickets structure. Finally, we write a very easy to use the toolbox. This is the GitHub homepage of our project. Basically, it's install free. We just put the Python file into the project folder and import them. You can using the DES API optimizer just as SGD in Python, in PyTorch. I'm also give some example to train the network by using internet dataset, which is this script. And our network optimizer can find important structure sparsity, have short train time, can explore the regression path, and a lot of interesting property. And we can also give the script to do the network pruning. Basically, by using the information from augmented variable gamma, we can do the network pruning. And we also can do the growing network. We add the new filter according to the support set of augmented gamma to enlarge the model capacity, which is a very interesting application. Basically, we can start from a very small network and using our optimizer to train the model, and then enlarge the model and train the model at the same time. So finally, we give some brief discussion about our our algorithm from ADMM, which is also adopts the idea of variable splitting. So the biggest difference is that ADMM is an optimization algorithm, which is convert to a minimizer of a loss with a fixed regression parameter. In contrast, DESI is a discretization of a differential equation, which generates a sequence of model from simple to complex, corresponding to different regression parameter. So the idea here, we basically care more about the regularized solution path. Okay, it's time I'll end here. So thanks. If any question, please email me, and let me check whether there's any question. Let me stop sharing. Okay. Any question?
Maybe I have one small question. Just now you mentioned the maybe the finding the sparse transformer, or before that some work you said maybe inspired by your algorithm. What's the idea of that application or that work? How this connection becomes?
Oh, you mean?
I guess it's somewhere maybe before the sparse transformer or something. Yeah, this one.
This one.
Yeah.
Right.
I guess. Yeah.
So, thanks for this question. Interesting. Actually, very interesting. Basically, we know that transformer has a lot of parameter, and basically we want to do the pruning and make a transformer sparse and make the transformer useful to a lot of like robotics or for self-driving car. The key difference that we are doing the learning sparsity on deep model by using our algorithm, by using our optimizer from a optimization perspective, rather than directly do the sparse, rather than directly design sparse transformer. So in this work, basically they design the sparse transformer, and it's kind of two orthogonal task, two orthogonal method. For this task, for this design sparse transformer architecture, they can also using our optimizer and optimize the model, and we can identify the redundant parameter and remove them. Yeah, it's actually the future work to give a more solid experiment to test whether optimizer can well be used to transformer. Right. That's my think.
Okay. Yeah. Thank you. That's very expensive for transformer training.
Yeah. But with the development of GPUs, I think it will be solvable. It's much cheaper. For example, like 2 years ago, 4 years ago, the GPU the GPU memory is compared with nowadays GPU memory is totally totally different. 4 years ago, we cannot afford to even train a transformer. Now we can do much better. Yeah.
Okay.
Thank you. Then let me Yikai, are you here? Let me
I'm here.
Sharing. Yeah, you can share. I think next talk is your talk, right? Next is your talk.
Can you see the screen?
Yeah.
Okay.
Let me briefly introduce you. Yikai Wang, third-year PhD student from my group. He published 3 journal conference papers, including 2 CEPR paper and 1 PAMI paper. His research interests including theoretical guarantee, machine learning algorithm, and application to computer vision and other artificial intelligence field. So let's welcome Yikai give the talk.
Okay, thanks, Yanwei. Hello, everyone. I'm Yikai Wang, a third-year PhD student with supervisor Dr. Yanwei Fu from School of Data Science, Fudan University. Following Yanwei's talk, I will spend 20 minutes to give a more detailed explanation on sparse learning for noise data labels part, mostly from the statistical perspective. I will introduce a simple yet effective framework for noisy data detection with application in different vision tasks. First, I will introduce what is sparse learning for noise data detection. What is noisy data? It may be the red apple surrounded by green apples. It might be the data that fall more than 3 standard deviations from the mean value, or it might be the point that's far away from the curve. Generally, noisy data or outliers are the irregular data compared with the majority of the dataset. In label space, noise data mainly refers to the mislabeled data. This noise may come from many aspects. For example, if the labels are randomly corrupted, then some irregular labels will lie in the label space. Humans are inevitable to make mistakes, so our annotations are not so credible. In some research areas, people will use a search engine to get training data. However, for example, if you search shotgun in Google, it may return a historical figure or a game character, but we usually only need one of them. Then the other one will be a noisy data for our target. Also, we may collect some complex or confusing images that are hard to distinguish. For example, this is a figure of dog, but it looks like a cat. Then what can we do to identify the noisy data in label space? To identify these noisy labels from the training set, we propose to use a simple linear system to model the relation between network features and one-hot labels. This linear system is known to be sensitive to noisy data. That is, the solution of beta is not stable as it may be influenced by even a single outlier. But actually, this is exactly what we want. Why do we use a linear system? For an ideally trained network, we have a softmax linear relation between feature vector and one-hot labels. If we approximate this by dropping the softmax operator, we can get the aforementioned linear system. This is a weak approximation, but this is helpful for our target. For clean data, this weak approximation is enough to model the relation between features and labels. But for noisy data, this approximation is biased, and a large fitting error will appear. Specifically, we add a noisy data indicator gamma to represent the noise data explicitly. For clean data, as we said above, the linear relation is strong. Thus, we should have a small or even zero gamma. If the data is noisy, a large gamma will be returned by the linear model to better fit the noisy feature label pair. Basically, gamma can be regarded as the residual predict error, which is a baseline method to identify noisy data in the training set. However, this residual fail to detect outliers at leverage points. Then a better way is to use a leave out externally student as the residual to test whether the predicted residual is large based on the other observations. This is equivalent to test whether gamma equals to 0 in this equation. But this can only be solved when there is a single outlier in the training set. When there are multiple outliers, we have two additional problems to solve. First is masking, that multiple outliers may group together to mask each other to be undetected if we only leave one of them in the statistical testing. The other is swapping, that multiple outliers may result in a large T for clean data, leading to a false discovery of outliers. Thus, we consider solving the whole indicator matrix for all training data at the same time, leading to this equation. Now our target is to solve gamma and identify noisy data based on the gamma. This noisy data will have zero solutions at the individualization. To ensure this, we add a sparsity to gamma, leading to this objective. As we only care about the solution of gamma, and it is known that beta is unstable and weak for classification problems with noisy labels. Thus, we first drop beta by solving beta with fixed gamma and transform this problem into the new problem where only gamma is unknown. And then we can simplify this equation into the new objective. This is a standard linear regression. Now, the only problem is how to choose the sparse coefficient lambda. A number of methods for determining lambda exist, but none is suitable for our formulation. For example, some heuristic rules on setting the lambda are popular in existing models, such as the M estimator, where the sigma hat is a Gaussian variance set manually based on human prior knowledge. However, setting a constant lambda value independent of dataset is far from optimal because the ratio of outliers may vary for different datasets. Cross-validation is also not applicable here because it can only optimize part of the sparse variables while leaving those held out validation set undetermined. But this held out validation set is also noisy. Data-adapted techniques such as scaled lasso and square root lasso typically generate overestimates on the support set of outliers. Moreover, they rely on the homogeneous Gaussian noise assumption, which is often not valid in practice. The other alternatives like AIC and BIC are often unstable in outlier detection lasso problem. Thus, it is very hard to choose the proper lambda in advance. This inspires us to sequentially consider all available solutions for all sparse variables along the regularization path by regarding the solution of gamma as a function of lambda. Then, when lambda turns to infinity, gamma will turn to 0. With a proper penalty, for example, the row-wise L2 vector norm, gamma will vanish row by row, that is, instance by instance. Then we can use the lambda where gamma turns into 0 to rank the data and denote the last vanished instances as noisy data. We call that in our motivation. Clean data will lead to a 0 gamma, while noisy data results in a larger than 0 gamma. Hence, in the solution path, clean data will vanish earlier, while noisy data will not vanish until a large lambda. This solution path can be generated by the GLMNet algorithm. This is the visualization of the solution path. The red line is the most clean data suggested by our algorithm. In summary, our proposed framework, instance credibility inference, assumes the linear relation between the features and one-hot labels, and we use an explicit noisy data indicator gamma to represent the noisy data. We simplify the linear regression model with gamma to linear regression model of gamma, and solve the solution path of gamma to rank the data and select the clean data for training, or in other words, identify and remove the noisy data. As we are a statistical method, we have very nice theoretical properties to identify the noisy subset. Our results based on the model selection consistency of lasso model. We assume that the random noise is RID 0 means sub-Gaussian noise. Based on this assumption, we can give 3 conditions, and we just translate the conditions into English. If we have C1, we can get a unique solution. If we have C2, clean data and noisy data are diverged to some extent. If we have C3, the error is large enough to be identified from random noise. Then Based on this condition, we could provide the following results. If we have a large enough lambda, and if C1 and C2 holds, then the noisy set identified by our algorithm is a subset of ground truth noisy set. If folder C3 hold, our algorithm will identify all the noisy data. As our theory mainly designed on the assumption of sub-Gaussian noise, we test by running 2,000 random tasks to check whether this holds in practice. The simulated distribution of noise can be roughly combined with 3 Gaussian distributions with further a near zero mean and limited variance, which verifies that our assumption is reasonable in practice. Now we introduce some applications of sparse learning in noisy data. We first introduce sparse learning in feature learning problem. Feature learning aims to learn a robust model with only a few training data available. If we consider the annotation cost, feature learning lies between unsupervised learning and learning from noisy labels, since we only need to annotate a few training data. But it is not just training with a few data. For example, the standard binary classification needs a lot of labeled data to model the decision boundary. When we only have a few training data, the decision boundary is very different, and we only have access to little information about the two classes. But feature learning aims to get the decision boundary in the left using only a few labeled data. This requires additional prior knowledge, like pre-trained with related datasets or with noisy unlabeled data. In industry, it is reasonable and cheap to collect noisy unlabeled data to support the learning model. In this scenario, we can use a self-taught learning pipeline. First, we train the feature models with the labeled image label pairs. Then we inference the two labels for unlabeled images. We can further train the feature models with these two labeled images. But in this self-taught learning pipeline, the core problem is how to ensure the retraining with two labeled images is trustworthy, that the retraining will not damage the capacity. However, this is hard to do as the two labels are very noisy. We will use the proposed framework to ensure that this selection is credible. Our framework repurposed the self-taught learning pipeline. We first encode the images into features. Then we train the linear classifier with the labeled image label pairs. The unlabeled images are inferred by the trained linear model. Then, to select the credible subset to expand the training set, we use the proposed framework to identify noisy data and remove them from the selected subset. Then we can retrain the classifier with these two labeled images. As we introduced earlier, we model the features and one-hot the two labels with the aforementioned linear system with noisy indicators. Then we solve this system and simplify this to a standard linear regression of noisy indicator. As popular approaches to choose lambda are not suitable in our case, we thus generate a solution path to better identify the noisy data. As visualized in this figure, where red lines are clean two labels, where black lines are mislabeled data, it is evident that in the solution path, most of the clean data will vanish faster than those noisy data. We can further extend the sparse learning framework to the logistic regression case. Similar to the linear regression case, we introduce the noisy indicator to the linear predictor. Then, with simple transform, we can get a standard logistic regression model with extended coefficients. Thus, we can use standard optimization algorithm to solve this model. Here we check out whether our theory and empirical results are matched. In more than half of the experiments, the assumptions C1 and C2 are satisfied. Most of them will achieve better performance after self-taught with ICI. Then, when all the assumptions are satisfied, we will get a better performance in a very high ratio. Even if C2 and C3 are not satisfied, we will still have a chance of improving their performance. Now we can further use this linear system in the problem of learning with noisy labels. Learning with noisy labels aim to learn a robust model from noisy training set. We combine the aforementioned linear system into learning the recognition model with noisy training set by iteratively do the feature learning and sample selection stages in the training time. In the first stage, the network is trained with cross entropy to extract features and classify labels. As there are noisy labels, the network is not well trained. To solve this problem, we need to identify noisy data and remove them from the training set. We assume the linear relation between features on one hot labels and those break this assumption will be identified as noisy data. We solve this linear model with sparsity on the noisy data indicators. With the solution path, we rank the data by their selecting time and remove the identified noisy data. This ends the second stage, sample selection stage. Then we return to the feature learning stage and repeat the two stages iteratively until converge. To make the linear system scalable to large datasets, we first compute the class similarity matrix and divide the most dissimilar classes into groups. For each group, we select a small number of training data to construct small pieces of data. Then our model is running on each piece in parallel. We also have some strategy to help train the network. To encourage the linear relation, we can put the sparse penalty on the output of the FC layer to get the sparse output. A sparse output before softmax operator with a small entropy cross entropy loss suggests that the linear relation is strong between network features and one-hot labels. To further exploit the small set of noisy data, we combine our algorithm with CAD-mix to further exploit the spot of noisy data by generating new training instances based on the interpolation of clean noisy data pairs. We test the label precision performance of our algorithm to check whether we can distinguish clean data from noisy data. In different settings, we can consistently achieve high precision, showing the capacity of our framework for noisy data detection. That's all. Thanks for listening to the talk.
Okay, thanks. Any question about Yinkai's probably since we are a bit late on the schedule, maybe if any question, please email us. Sorry for that. I found that I just realized that I got 20 minutes late than schedule. Professor Yuan, are you here?
Okay.
Yeah. Can you share screen? Yeah. Okay. That's great.
Okay. Is that clear?
Yeah, that's clear, but not full screen. It's just a PDF, right?
Just PDF. I mean,
do the full screen. Maybe you want to do the full screen or not?
Full screen. You mean?
Yeah, full screen.
This is already full screen in my side. Is that okay? Full screen for you?
Okay, maybe that's cool. Actually, that's the bookmarks on the left part.
Bookmarks.
Yeah. This part is open.
Or you can type command plus L. Command plus L.
Yeah.
Is this better? You can, or maybe you can still see the bookmark.
Yeah, that's cool. I think that's totally okay. Okay, let me introduce. Yeah, let me introduce Professor Yuan Yao. Professor Yuan Yao is with the Hong Kong University of Science and Technology. Received his BSc, MSc in Control Engineering both from Harbin Institute of Technology, China, in 1996 and 1998, and MPhil in Mathematics from City University of Hong Kong in 2002, and PhD in Mathematics from University of California, Berkeley in 2006. Since then, he has been with Stanford University, and in 2009, he joined the Department of Probability and Statistics in School of Mathematical Science, Peking University, Beijing, China. He is currently professor of mathematical, chemical, biological engineering, and biochemistry, computer science, and engineering, Hong Kong University of Science and Technology. His current research interests include mathematical modeling for high-dimensional data analysis and statistical machine learning with application in computational biology, computer vision, and information retrieval. Okay, thanks. Let's welcome Professor Yuan talk. Okay.
Okay. Thanks for Yanwei's introduction. I will try to give a fast talk because the time is delayed. So this is, hopefully you can see this screen well. This is about the inverse scale space method for sparse learning. And mostly I focus on the statistical property. And maybe you heard those inverse scale space name before or may not, but it's not so strange for you. Actually, you have been touching this kind of dynamics one or twice in applications in other scenarios with different names. Some people call it mirror descent. Some people call it linearized fragment. So anyway, let's see the detail. So here, I would like to thank all those collaborators, and particularly today, Watao and Xinwei and Yanwei, they all present their works. And so here, this is the content. So first, I will try to give you some illustration or demonstration using R package and Python package. I think Yanwei already showed this DESI LBI Python package. Just show some very fast browse of these results to motivate what we are going to talk. And the second part, this is the most important thing. We want to show how the inverse scale space arise as a dynamics from lasso, very classical lasso, because lasso has bias issue, and to overcome the bias, then we can develop some differential inclusion dynamics. So
sorry, Professor. Yes. It seems that your on my side, your slides is still on the first page.
Oh, really?
Yeah, the title. I don't know whether it's. Oh yeah, yeah. That's good. Yeah.
Oh, I see. So maybe I cannot. Now, if I move, does that work?
Yes.
This is a new page, right?
Yes.
Okay, then maybe I just use this format. Maybe I cannot use the share full screen mode. That doesn't work. Okay, let's see this is the content, and I just now I say the second part is how the inverse scale space arise from lasso as a differential inclusion dynamical system. So this is a crucial part. And the next part is how the variable splitting was introduced into this classical inverse scale space, such that we can achieve some weaker condition for feature or variable selection problem. And this is how the DESI LBI, those split LBI, those type of algorithm are derived. And that's the kind of the main summary. And now let's see the first package. This is our old package, CRAN-R package called linearized fragment algorithm, and mostly done by some former students before Renfeng. He is now become soon to be the faculty in Northwestern University, and Jie Chao, he's a researcher in Tencent, and this is my old picture. And in this package, actually, we include several sparse statistical model that was widely used today, including some application like noise, outlier detection. So in this package, that includes the linear regression, and we are going to use inverse scale space and the linearized fragmentation. You will see in that, and logistic regression and graphical models. And we include two types of regularization, like lasso and group lasso. And so this is the one line, maybe two line code for the central algorithm in this package. Just these two line codes. The first line is simply a gradient descent. Loss can be all the previous example we have mentioned. And the second line is a proximal map. So here we can use those penalty like L1 or group L1, or maybe something more complicated than that. And these are the parameters. Alpha is the step size, and kappa is a constant such that the product of step size and kappa with this Hessian matrix 2 norm must be smaller than 2 for stabilization. And this is looks like in the first side, looks like very similar to ISTA, iterative source thresholding algorithm. However, you will see soon that this algorithm have very different limit dynamics. What I mean by limit, I will show you soon. And for linear regression, actually, we can do this kind of linear regression model, use some group penalty or ungrouped, that's plain L1. So we apply this, you can use this line in R to apply that to diabetes data, which is very popular in statistics since Bradley Ifron first published paper based on this data. And here, this is the, if you are familiar with a statistical learning textbook, then this picture is looks very familiar to you. The top left is the lasso. We call the lasso regularization path. X-axis is normalized to be each of the beta, its absolute value, the absolute value of the coefficient divided by the max of beta 1 norm. And this is the normalization. And if the curve actually appeared early, like these two green curves, that means that these variables are very important, will be selected earlier than the late variables. So that's the lasso regularization path. The variation, the x-axis, the change is due to the lambda or regularization parameter change, although we use some different normalization as the different coordinates as the x-axis. On the right, this is called the inverse scale space method using the L1 penalty. So you can see the curve are very different to lasso. However, the order of those variables becoming to be non-zero bear a lot of similarity with lasso. So still the green curve appeared earliest than others. They are the most important variables. And below we call that's linearized fragmentation. That's the two-line algorithm I showed you just now. And basically, you can see when kappa change from small to large, the curve shape may change. However, the order still very stable in terms of which one becomes non-zero first. So this is looks very interesting how this happened. And later we are going to tell you some story, but before that, we can take some further example like logistic regression. Of course, this time we changed the model as well as the loss, but the penalty are still the same. And then if you apply this logistic regression to some real world example, so here is a data set. We call the COPS winner publication called data set. So Professor Jiashun Jin from CMU collect 3,000 papers, about 3,000 authors in the major statistical journals. And we select a subset of 382 papers. They are co-authored. They are authored by 35, include the author of 35 COPS award winner. That's the statistical, the highest prize in statistics. And this is the co-authorship network. You can see this graph is very sparse. The question is, can we model the co-authorship structure to predict whether in the future two authors would like to collaborate or co-author a paper or not? What's the probability? So this is the kind of question. And basically, we pick up one famous statistician, Peter Hall. Unfortunately, he already passed a couple years ago in the pandemic season. And we pick up this Peter Hall, that's the, say, target response variable. And we ask how the other COPS winner scholars collaborate with Peter Hall. And the right picture is the co-authorship network. You can see Peter Hall only collaborate with three people, three scholars in the data set, Jianqing Fan and Tony Tsai and Carroll, RJ Carroll. So if you run a logistic regression with all the other authors target to Peter Hall as the response, you can see this kind of curve. The x-axis represent the solution past the iteration. That means if you iterate this algorithm, you will basically see those curves along the iteration. And the particular three curves, those three color curves, that exactly correspond to the three collaborators, Jianqing Fan, dash right here, and Tony Tsai, the dotted red here, and another is Carroll, Raymond Carroll, that's the purple curve here. So they are kind of leveled, appear to be non-zero very early, and becomes leveled, showing that these three curves will be true collaborators. And all the other curves actually can be arbitrarily small if you iterate. That means they tend not to collaborate with other, also tend not to collaborate with Tony, with Peter Hall. So this is an interesting logistic regression with the regularization path using our algorithm. If you are not that clear, maybe we can do a more complicated model. We ask the pairwise interactions from all the data. So this is called a sparse Ising model, a statistical physics model. And in this Ising model, the likely probability of P authors, whether they co-author a paper, subject to this probability model. And HI measures the mean rate, and Jij describe the interaction between Xi and J. So if we ask whether two authors collaborate, then basically we ask whether Jij is +90 or not, the sparsity of J. So we say if Jij is larger than 0, then that means also I and also J tends to collaborate more often than others. Otherwise, if less than 0, then they tend to less collaborate or collaborate less frequently. And if they just equals to 0, that means these two co-authors does not have interaction. So if you look at how this algorithm works on this model, here is a simulation. Simulation means we generate the data using a 2D grid Ising model. And on the right, we try to use this algorithm using such simulation data, try to recover this grid. So this is a movie. Just be patient and let me click. You can watch what will happen. So you can see lots of the 2D grid will be rapidly formed during the iteration. And if that will be stable. If you wait further, then there will be some light lines which are crossing different large scale interaction. But those are not true interactions because we know the ground truth model must be on the left. And if you see this right model learned during the iteration, that means that you learn some fake interactions or noisy interactions. So this is how we illustrate this algorithm. If that iterates, somehow the dynamics will first give the true signals or true interactions and then learn the noise or generate the fake interactions. And we want some sparse model along this iteration process. That means we want to model the true interactions, then we need some early stopping. So this is the intuition behind how this algorithm works. So now, beyond this simulation, we apply this data, this algorithm to the corpus data. Let's see what will happen. Right, this the true collaboration network. The left is what we are going to use the algorithm to iterate. So let's see what will happen. So the first three interaction exactly rapidly formulate. And then there are lots of other interaction, much dense, but mostly they are red in the sense that the Jij will be negative. A few of them will be positive, means the Jij will be green. That means Jij will be positive. Positive means that they are more often than average, but the red color means they are less often collaborated than others. So you see the same phenomena as before. From this data, if you run this algorithm, if we run this algorithm without early stopping, then that converge to something overfitting the noise. However, if we early stop that, we can capture some true or faithful interactions between the authors and make some good predictions. So this is the kind of phenomena I want to highlight using this illustration to highlight. And everything we are going to talk about that later is about early stopping, how the early stopping can be used to avoid overfitting the noise and return some true sparsity, or say causal relationship between the in the models. Okay, so this is the slides that Yanwei already showed you before, and compare this picture compared the Euro stochastic gradient descent method and the training path using the split LBI, decile LBI. I'm going to talk about the math after that, but I think Yanwei already showed that. So the right, that is the filters, important filters selected. That's the convolution filter selected along the split LBI, along the early epochs. So there are three stops at the epoch 20, 40, and 80. So you can see the selected filters are kind of highly concentrate on some particular patterns. However, if you run the stochastic gradient descent, they are not so specific. The filters, basically, there are a lot of many different filters. They are kind of dense. This one is kind of sparse. So from compared with previous examples, though this illustrates that those are the most important filters discovered by decile LBI, such that the performance will be the same. With this subnet, the performance accuracy will be similar to the full dense model. So this is the picture for MNIST dataset. However, if you do the same experiment using the ImageNet, the things are much more intrigued, because this is on the bottom line, this is the SGD, stochastic gradient descent. On the top line, they are the decile LBI with two different kappa. So you can see they also select some sparse filters, but the most important filters on the top left, the least important will be on the bottom right. So you can see the most important filter is a kind of texture features. rather than the color or shapes. Color or shapes will be on the bottom right. So this actually tells you the ResNet 18. This is typical deep network trained on ImageNet. It's not using the clues like human to recognize the image. They are using some high order statistics featured by texture patterns rather than the color and shapes. Those are least favorable in this selection process. Okay, so I think this is somehow trying to give you the idea how the early stopping can be used here to select important feature or causal feature in your models. Okay, so how this kind of picture really, how does it work in theory? Below, I'm going to show you some story from statistical point of view. Basically, that's a statistical model selection consistency under the early stopping regularization. So what I'm going to show is first the simple iterative algorithm in the very beginning, and including other talks EMA showed other type of algorithm. So this simple algorithm shadows a particular kind of dynamics. We call that that's a kind of inverse scale space described by differential inclusions. So they are the special case of mirror descent. If you are coming from optimization society, you can find very close. There are some important particular case for mirror descent algorithm. So in this type of inverse scale space algorithm or dynamics, important features usually are learned fast or faster than the non-important ones. So you see many different examples before what I mean by important or not. They in different application scenarios, they refer to different intuition. And so this simple algorithm, of course, very easy for parallel implementation for large scale applications. And in statistics, we are going to show that in the basic format, this algorithm works under nearly the same condition as lasso in terms of variable selection that reach the model selection consistency if a proper early stopping rule is given. And this algorithm, this dynamics actually can have been less biased than lasso, so that's the advantage. However, if we are equip them with variable splitting, this algorithm can weaken the condition of, say, generalized lasso. So it's more general version of lasso in feature selection. So in that sense, they can be better than lasso in terms of model selection consistency. So this is the rough picture. I hope I can rapidly cover some of the core material without mentioning too much detail. And we basically talk about, when we talk about the theory, it's about two things. One is sparse linear regression. We call the basic sparsity in the sense that y equals to x beta star plus epsilon, and beta star is sparse. Just a few of them will be non-zero. We take the support set to be S, and then complement null set will be T. And another scenario is the generalized structural sparsity or transformational sparsity. It means our sparsity is not on beta star itself, it's on a linear transformation, D beta star, gamma star. We call that gamma star. That is a sparse. We call this transformational sparsity or structural sparsity, and also study its support set, gamma star. And both will be useful. And the question is how to recover the sparsity pattern. Statisticians call that sparsistency. And so that's the issue. And so the first issue for this kind of question is even you know the support set, true support set, you don't know this one. So if the God revealed support set S2U, then we call the estimator to be the oracle estimator. You can never do better than oracle estimator. That's the subset least square estimation using the support information. So that gives this one. So this oracle property means that you always have model selection consistency because support set is the truth, and the estimator is asymptotic, is a normal subject to normal distribution with the mean equals to the beta star. That's the ground truth, and this is the covariance matrix. And this oracle estimator is unbiased in the sense that its mean is the ground truth, but you never have this oracle estimator because you never know the support S. You have to estimate S in practice. So people usually use lasso as L1 penalized the least square problem. So here I write T as the regularization parameter instead of lambda multiplied by L1 norm, usually used by statistician. But this T is for comparison with inverse scale space to illustrate the idea. And this kind of optimization is very popular in statistics. People usually started using the first order KKT optimality condition, first order optimality condition, 3A and 3B. If you take subgradient with respect of this L1 norm, then that gives 3B, and on the other hand, it gives you the first order derivative mass equals to 0, that's gives 3A. So that characterizes the property. But the well-known issue for lasso, if you solve this KKT condition, lasso is always biased in the sense that you can see a particular example using X equals to identity. That's the identity design matrix with single sample, single dimension. Then the lasso estimator must be this closed form. If tau, this is the regularization parameter. If tau is less than this param 1 divided by oracle estimator, then bit hat equals to 0. This is the lasso estimator. Otherwise, this is equals to oracle minus 1 over tau. Tau is a fixed amount. It's a regularization parameter. So this never satisfies the expectation of bit hat equals to beta star. So this is the unbiased issue. So this is by Wotal's picture as the illustration for the bias of lasso. The blue is the lasso solution. It's kind of shrink from the ground truth. And in this kind of scenario, even you know the oracle, even along the lasso estimator on the path, you know at certain path point you reach the support recovery, you know the oracle support of S. Then the lasso estimate is, in the general case can be written as the oracle estimator minus this is the bias part. This is the red is the lasso bias part. Then the question is how to remove the bias. Can you have an easy way to remove the bias? And in statistics, people develop non-convex regularization using, instead of using L1 norm, they use a Q penalty, LQ penalty, such that in the general shape like this solid curve, starting from Zhenqing Fan a long time ago. And but this question is it's non-convex optimization. Usually it's hard to locate a global optimizer. We have to ask under what kind of condition all the local optimizer gives statistically good estimator. Of course, how to describe statistically good will be an interesting problem. And for another idea comes from applied math. So let's see how this idea developed toward the inverse scale space. So this one, if you start from lasso, take a first order KKT condition, you get this one. Rho T is a subgradient beta 1 norm. and the right-hand side is just a gradient of square norm. And if this KKT condition, because both sides depends on parameter t, that's the regularization parameter, we can formally take derivative with respect to t. And the left-hand side becomes rho t derivative, right? This is the right-hand side. And beta t and t, these are two terms depending on t, so you can take derivative like this. So with this, you can actually have a plug in something. Assume at certain point, say at tau n, t equals tau n in the neighborhood, we achieve the sign consistency in the sense that rho tau n equals the sign of beta star. So whenever I lies in the support set, that must be plus or minus 1. Otherwise, that's equals to 0. So the rho dot, because it's constant plus or minus 1, then if you take derivative, must equals to 0. So in other words, this one must, if you solve this one at this sign consistency, then the blue part must equals to the oracle estimator. So this actually gives you an automatic way for debiasing. So in other words, if you recall that the previous lasso formula, this is the lasso estimator equals to the oracle estimator minus the bias. So if you plug in this one into this blue part, take the derivative with respect to tau, then you immediately cancel the red part, the bias. You get this oracle estimator. I think this is all the key idea for this, maybe for this this theoretical part, because that tells you how to do the debiasing. And this is the, if you formally write down this idea as the, this is called differential inclusion. This is exactly give the differential inclusion like this. If you take the lasso KKT condition and the rho dot t, that's the derivative with respect to t. Compare with lasso KKT condition, this one is on the bottom. So this kind of dynamics first arise in applied math called the inverse scale space, because the important feature or coarse-grained feature in image recovery appeared first along this iteration, just like various examples we see before, and then the fine detail appears in the later. So these are the firstly appeared in image recovery. But of course, this connection with lasso is from modern statistical point of view. And so here is the solution that doesn't have this bias, and you can see get a closed form solution, debiasing as desired. And to solve this mass solution dynamics, we can use a sequential restrict maximum likelihood estimate. So that I can skip this. And this is the comparison on the diabetes data with lasso and this inverse scale space. You can see this inverse scale space is piecewise constant rather than piecewise linear in the lasso. However, their order will be the similar. And why the order will be the similar? So here we can share with you a past consistent theory in the sense that there is a nearly the same condition called a incoherence condition for sign consistency of lasso. The solution path contains some particular point, those points which are sparse and sign consistent. And once the sign consistency is met, there must be the oracle estimator, which is unbiased. So that's the kind of thing. And the early stopping is all you need to find such point. So here are the conditions, assumptions to show the theory. We need a restricted strongly convex, means the Hessian matrix of the square laws restricted on the support set must be positive definite. And second, they call the incoherence of a representable condition written in this form. That's the same as lasso. and the rich literature studied that. And inverse scale space actually is a kind of restrict gradient descent in this sense. So because you have the incoherence condition, and that ensures your dynamics will first go gradient descent in the support set of the of your signal. That's called oracle sparse space, oracle subspace. And because the loss is restrict strongly convex in this subspace, so you have exponentially fast decay toward the saddle point or toward the local minimizer in this subspace. And then the early stopping can avoid you go to beyond this oracle estimate, this subspace. You find this saddle point that's the oracle estimator, and the early stopping avoid you to go to escape from this subspace to find noise. That's the intuition of this kind of inverse scale space as restrict gradient descent. So mathematically, this is the theory. Basically, that says this is the early stopping time. Before this early stopping time, you won't have a false positive in the sense that you always evolve in the support oracle subspace. And then you find if the signal is strong enough in the sense that the minimum magnitude is larger than this lower bound, then at this early stopping time, you can reach the sign consistency. Then you find the oracle estimator. This early stopping time, of course, depends on the incoherence condition eta and other parameter, which is not decidable in practice. But later we can say we can use some data adaptive rule to decide the early stopping toward the false discovery control. But that's the main theory, formalized idea. And you can design a fast, large-scale algorithm from this dynamics. So because the dynamics piecewise constant, you first make it continuous by adding this 1 over kappa damping term, and then use forward Euler discretization, then get this algorithm that's called linearized Bregman iteration in literature, invented by Wattal, Yin, and Osher group long time ago. And so that's the two-line algorithm I written in the very first slides in the beginning. So we can skip that. So here, what's the difference between this algorithm with ASTA? ASTA actually only solve a fixed one penalized problem. So this is the ASTA algorithm that solved the lambda regularized lasso with regularization parameter lasso lambda. And if this iteration goes to infinity, that solve this one. If you want to find the regularization path, you have to take a grade of lambda k, then solve ASTA parallelly and until convergent. However, this linearized Bregman, although looks like quite similar, in computation cost, they are indeed the same. Just a single run of this algorithm that returns the whole regularization path. That's the crucial difference between the ASTA and the linearized Bregman. Okay, so here is the illustration for generate the regularization path and maybe less bias, as I mentioned before. This is the path consistency in discrete setting. I think you can also generalize this to general laws and regularization. I won't talk about too much detail here. The summary about the generalizations. And one thing particularly I want to mention is how about the transformational sparsity? If you have this gamma star equals d beta, instead of beta star to be sparse, gamma star to be sparse, what will happen? And this is the comparison between generalized lasso and split lasso. So generalized lasso comes from statistics. So this d beta one regularization, and the split LBI, this one take a relaxation of gamma minus d beta. in the neighborhood, Euclidean neighborhood, instead of exactly debit. So then apply the linearized Bregman on this new laws. So that's the crucial difference. And with this difference, actually, you can show that the new relaxation actually can improve the performance in terms of variable selection. So this table shows that with new increase, actually, you can increase the power of variable selection or model selection. And why this happened? Because variable splitting may induce a weaker irrepresentable conditions than generalized lasso. So that's the key. So I think I may simply skip this one that simply says the necessary sufficient condition for split LVI is called this represent condition, a representable condition and the family of nu that can be strictly lower than the generalized lasso. The IC1 is the generalized lasso condition, and this blue curve is the IRR for nu. If nu enlarge, that could be strictly smaller. Okay, and as a result, you can prove similar statistical path consistency for this kind of condition. And in particular, along this split lasso, you can reach this no false positive property and sign consistency and L2 consistency. And of course, the cost of this enlarging nu no free lunch may increase the L2 error. And you need to project back of this L2 error to the sparse kernel, sparse support set. Then you can recover this minimax optimal rate. So that's the main statistics. I think we have many applications, but we don't have too much time. This is Yanwei show this algorithm in the neural network, finding the lottery ticket using early stopping. I think next talk, Xinwei will talk this Alzheimer's disease detection. And finally, as I mentioned, in the very beginning, the early stopping time in our theory is not known in practice because of incoherence condition is not known. But fortunately, we can use a knockoff idea developed by Barbara Candice toward the data adaptive early stopping rule. So if you are interested with this development, you can refer to this our recent paper with another student and Xinwei. I think I can take a stop here. So basically, in this short tutorial, we show you the limit of linearized Bregman iteration follows some differential inclusion of inverse scale space, we call that. And the most important things is significant features emerge earlier on solution paths. And you need some early stopping to avoid overfitting noise. So this kind of dynamics can render unbiased oracle estimator under the sign consistency, the same condition as lasso. But if you use the variable splitting, you can work under a weaker condition than generalized lasso, achieve the sign consistency. That's the main theory. And if you are interested, you can take a reference list to see the more detail. Sorry, I'm over time, but hopefully save some time. I think I should pass it to the Xinwei for the next talk.
Thank you, Professor Yao. I'm the host of the second half of this tutorial, and hello everyone. And I will briefly introduce myself. My name is Xinwei Sun from School of Data Science in Fudan University. I'm currently an assistant professor, and before that, I work in the Microsoft research. my current research interests include causal inference and also the sparsity high-dimensional statistical learning, and with their applications on medical imaging and machine learning. Okay, so in the previous talk, Professor Yuan Yao introduced the theorem of differential inclusion for the structural sparsity. So in this tutorial, I will follow to introduce some details and how they can be applied in the medical imaging scenario. And today's talk is divided into 3 parts. I will first introduce the structural sparsity problem in the medical imaging field and their related work. And then I will introduce for details how the differential inclusion can address this structural sparsity problem. And we can theoretically prove that this new method can recover the true positive set. It means that we can achieve better feature selection result and the relaxed incoherence condition than generalized lasso. But however, this condition is practically unknown. So therefore, in the last section, we turn to introduce our method to control the false discovery rate. We focus on the diagnosis problem, which mainly considered the 2 problems, the disease prediction and feature selection. Formally speaking, given the P covariance that can be extracted from the image, the medical image, we want to predict disease status and also select those variables which are disease related. For instance, in the Alzheimer's disease, as shown in the bottom left region, which is called hippocampus, compared to the normal control in the left figure, the patient can suffer from gray matter volume degeneration. And because the hippocampus is responsible for memory and language processing, the patient can suffer from memory loss. Okay, so therefore, it is expected that the model can not only accurately predict the disease, but also can identify hippocampus as disease-related regions. And besides, we can also see the lateral ventricular is enlarged and compared to the normal control. And this is thus can be utilized for the disease prediction. And during gray matter volume preprocessing, some voxels surrounding the lateral ventricular can be mistakenly included as gray matter voxels. And also, this phenomenon can be also seen at the space of the gyrus, which can be also enlarged than the normal control. So in total, there are 3 types of structural sparsity. The pure sparsity means that only a subset of features are disease related. And spatial coherence means it is in neuroimage analysis, adjacent regions, brain regions or voxels have similar brain activity or degree of degeneration. And thus we can regard the whole brain as a graph over all voxels, in which 2 voxels are connected if they are adjacent. And this graph can induce the fused lasso penalty, and we will introduce later. Besides, as the disease-related gray matter voxels are generally atrophied, the more degree of atrophy, the higher probability for the patient to be diseased. So there is a positive correlation between disease-related features with the disease label. Previously, there are several sparse learning methods in the Alzheimer's disease. For instance, the lasso uses the L1 penalty, and the elastic net further utilize L2 penalty, which can select more features. And the graph net generalize the elastic net from the L2 penalty to the one that on the graph on the transformated vector by the graph difference operator denoted by D. And the generalized lasso can replace the L2 penalty of the graph net with the L1 penalty for strict smoothness over the graph. And finally, the non-negative fused lasso additionally incorporate the positive constraint. Empirically, this method can perform very good, but they can also suffer from some limitations. The first limitation is the incoherence condition, which is statistically that can guarantee the true positive that, or in the Alzheimer's disease scenario, the disease-related features to be selected. This condition may not easy to be satisfied. And also, the second limitation is it overlooks the gap between the prediction and feature selection. They always equalize the two targets. And specifically for the second limitation, we observe that there are some enlarged gray matter voxels that can surround the lateral ventricular region or other the space of gray matter, the space of gyrus. And because these features are introduced in the procedure of preprocessing, so we call them procedural bias. And this procedural bias actually accounts for the gap between the prediction and the lesion features. So they can additionally provide a help for the disease prediction. And this is the result of feature selection of our method compared to others. And as illustrated, our method can, which called split LBI, can stably select the two-side hippocampus. Compared to others, in comparison, other methods can select some redundant regions or scatteredly distributed voxels, which are unexplainable. And also, in addition to the lesion features in the two-side hippocampus, we can additionally capture the procedural bias, which are enlarged voxels, and this can provide additional help for the prediction. So as illustrated, our method, when applied to the ADNI dataset, can achieve better result than others, specifically by than the generalized lasso. So in summary, our method can achieve can utilize procedural bias for better prediction accuracy and also select achieve better feature selection results. So next, we will introduce how do we overcome these limitations of the previous methods and achieve this promising result. We consider the recovering the signal beta star from the linear regression model, and where X is the design matrix. And here we consider the structural sparsity problem that after a transformation induced by the D matrix, the signal is sparse. And different transformation matrix can correspond to different problems. For instance, the pure sparsity, wavelength smoothing, and image denoising problems. And our goal is to recover the sparse pattern of the gamma star and also estimate the true values of the signal, which are respectively the sparsicency and consistency problems. And there is a large literature in it in this to study this problem. And perhaps the most popular one is the generalized lasso, and which has been studied in the form of total variation, fused lasso, or the pure sparsity. But there are two problems for the generalized lasso. And the first one is a computational issue that one has to run several hyperparameters to achieve the optimal result. And the second problem is the most key one, that incoherence condition, which is necessary for the true signal set to be selected, is difficult to satisfy. So our solution to attack this problem is by introducing another parameter called gamma star, and we relax the linear constraint between the gamma star and the beta star via the variable splitting term. And the new hyperparameter nu here can actually control the distance between these two terms. And then we, with this loss function, we run the following differential inclusion. And we will show later that such a three-line differential inclusion can have the inverse scale space property. And this differential inclusion is called split-Bregman inverse scale space, and it is composed of two parts: the update of the beta and the gamma. And for the update of the beta is very easy because it can be solved directly from the loss function by setting gradient to be 0. And for the update of the gamma, we introduce another parameter, which is the subgradient of the absolute value of the gamma. And this is the function of the absolute value of the gamma, which is differentiable except for the 0 point, and at which it has subgradient from -1 to 1. So in this regard, its subgradient it is belongs to -1 to 1, and as long as it is strictly in the interval from -1 to 1, and the corresponding value of the gamma is 0. So at the very beginning, the row start from this, it is set to 0, and it undergoes the gradient descent flow. And as it iterates until it reaches the boundary of the 1, the corresponding element of the gamma will be selected to be non-zero. And so the t here can be regarded as the regularization parameter, because as t increases and more and more variables will be reached more variables will reach the boundary and will be selected to be non-zero. And we can additionally consider another L2 penalty with a damping parameter kappa, and to approximate the original L1 penalty, and we can also obtain the subgradient. And as illustrated, the gamma can be inversely solved from the z, because as long as the gamma is from the -1 to 1, and the z is from -1 to 1, the gamma is 0. So this is basically the self-thresholding, and we can also we can solve the gamma at each time step, and this can induce a simple discretization version, which is called split linearized Bregman iteration. So briefly called split LBI. And this is the solution path of the split LBI. And at the very beginning, when t equals to 0, and no variables are selected, but as iterates, more and more variables will be selected to be non-zeros. But unlike the traditional optimization algorithm, which focus on the final step of the convergence property at the final step, we must be careful, because the final step can pick up the information of noise, which will cause the overfitting of the model. So we must alternatively choose the early stopping mechanism that before these times we can hopefully pick up the signal information. So the guarantee of this of this early stopping mechanism is to the early selected features belong to the true signal set. So it's a natural question. And this is the high-level intuition of our theoretical result. And we call the space Arco space as the space expanded by the true signal set, and its complementary set is called overfitting space. And the irrepresentable condition means the orthogonality between these two spaces, and it can ensure the loss functions at the very beginning to track on the Arco to decay at the Arco subspace until to the saddle point, which is unique if we further assume the restricted strongly convexity. And after that, we pick up the information of noise. So which means we start to overfit. And formally speaking, recall that our algorithm introduced the hyperparameter nu in the variable splitting term that relaxes the linear constraint. So, so the formally our irrepresentable condition, it means the IR nu is less than 1. And to illustrate why this condition is can be easier to satisfy if we increase the hyperparameter nu, we calculate the angle between the space of the overfitting subspace and the oracle subspace. And it is shown that as nu increases to infinity, this angle, the limit of this angle approximates to the 90 degree, which means these two spaces are orthogonal as nu increases. So we can theoretically prove that compared to generalized lasso, when nu equals to 0, our irrepresentable condition equals to the IC condition in the generalized lasso. And as nu goes to infinity, this condition can be easier to satisfy than the IC value, as long as the kernel of the X, the space of the kernel X belongs to the space of kernel of the D restricted on the support set. And this condition is equivalent to the restrict strongly convexity. So under these two assumptions, we have the following theoretical result. This has been introduced by the Professor Yuanyao. And we have conducted some simulation experiments that as the hyperparameter nu increases, we can achieve better variable selection results. And specifically, as nu increases, the AUC can be better. And this can be explained by the left figure, and in which we plot the IC condition of the generalized lasso and the IR condition of our split LBI. And at the very beginning, when nu equals to 0, our irrepresentable condition coincide with the IC value, and they are both larger than 1, which means the conditions are not satisfied. But as nu increases, our curve can finally be less than 1. It means that as long as nu is large enough, our condition can be easier to satisfy than that of the generalized lasso. So in addition, the variable splitting term can explore beyond sparsity because the beta here is non-sparse. So if the nu is large enough, it relaxes the constraint between the d beta and gamma. So the beta has more degree of freedom to capture more information. In the Alzheimer's disease scenario, it correspondingly captured the procedural bias to improve the prediction power. So in summary, we proposed the differential inclusion, which is a regularization solution passed via differential inclusion, and more variables will be selected as iterates. And earlier selected features belong to the true signal set and the weaker irrepresentable condition. And also the variable splitting term can enables to explore beyond sparsity to achieve better result in real scenarios. But practically, even the irrepresentable condition is weaker. The incoherence condition is also unknown. So we should come up with some ideas to control the false discovery rate. So in the last part, I will briefly introduce two methods for the FDR control, which are respectively from the wrapper method based on knockoff and from the perspective of empirical Bayesian. We first reviewed the previous work of the knockoff. It is a wrapper method for knockoff for FDR control proposed by Barber and Candace, and it considers the FDR control for pure sparsity, and the goal is to control FDR, which is defined as the expected ratio between the null feature among selected features that less than the desired level Q, for example, the 0.1. And then the idea of knockoff is like this. For each feature xj, it create a knockoff copy x tilde j as a control. And then it implements some black box algorithm to assess the zj and z tilde j, which are if respectively the effect of the xj on y and the effect of x tilde j on y. And then it compares the effects of each feature and its knockoff copy. For the non-null feature, the original effect on y, the original effect on y for the feature j, it tends to be larger than its copy. So also it has a larger effect than the null features. So for non-null feature, the wj it tends to be greater than 0 and large. But for null feature, the original feature and its copy has comparable effect. And this is the one property of the exchangeability property. It means that if we swap if we swap the null features to its copy, then the distribution of the W remain the same. So it means that for the null feature, the original feature and its copy have comparable effect, and the Wj has equal probability to be positive or negative. So as illustrated, the non-null features are restricted on the region of positive and large for the W. And so the knockoff selects the variables that are positive and large, and this it turns out to can control the FDR because for the null feature it has equal probability to be positive or negative. So they have equal distribution, and it can be upper bounded by the estimated false discovery proposition. So so theoretically, it can be proved that given any desired level Q, the knockoff can control the FDR. But for the structural sparsity, if luckily we can have the full column rank of the D matrix, we can inversely solve the beta from the gamma from the beta from the gamma. So we can also adopt the standard procedure of knockoff. But when the D is not full column rank, or M is larger than P, the M here is the row number of the matrix D, and we propose a joint optimization setting that over the beta and gamma. But here the noise variable is no longer homogeneous. And similarly, we can construct each copy for the X gamma, but the exchangeability fields, for instance, for each feature, we can calculate the effect as the largest hyperparameter for the gamma to be non-zero. For if we implement the generalized lasso. But as illustrated, the exchangeability no longer holds, because for the null features, they have larger probability to be negative, and they have larger magnitude. So to resolve this problem, we propose to compare to the original definition of the W. We propose to truncate the probability for its copy to be greater than its original feature, and then we truncate the magnitude when the copy is greater than the original feature. But there is another problem, that the null statistics Wj are no longer independent. If we look at the KKT condition, for the KKT condition, the knockoff copy has additional term, the zeta, and so condition on the z on the C, which is dependent on the noise variable, the probability for the W to be positive is equivalent for the is equal to the probability for the zeta to be negative. But for if we consider the zeta itself, it is unbiased, and the variance is diagonal. So it means that they are independent from each other. But if we condition on the C, these two properties are no longer hold. So we propose, inspired by this KKT condition, we propose to split the original data set into two parts, and we calculate the beta lambda from the first part, and also we access the ZJ and Z tilde J from the second part. So in this regard, the C is only dependent on the first part, and the second part because it is independent from the first part. So it means that the zeta we should no longer condition on the C to equalize the probability for the zeta and the W. So this means that the null statistics of the W are independent with each other, and we can theoretically control the FDR. And on the simulation experiments, we work well on the three scenarios for the structural sparsity. And we apply our method on the brain region selection and the connection selection for the Alzheimer's disease. We highlight the selected brain regions in the red and the bold edges to mark the selected connections. And each connection means it involves two regions with different degree of degeneration. So as illustrated, we can select the hippocampus and medial temporal lobe, which are believed to be the early damaged regions, and also the connections can also involve these selected or damaged regions. But the knockoff requires the number of samples greater than the m plus p. But in high dimensional analysis, the power is limited, and this condition does no longer hold. As illustrated, we apply the speed LBI on the V8 and V4 dataset. On V8 dataset, we have 2,000 voxels, but on the V4 dataset, we have 20,000 voxels. But even if more information, our prediction power decrease. So it is at first glance, seems a little bit surprising, but this can be attributed to the multicollinearity problem of the multivariate regression model. And this is the illustration of our feature selection result. And for the speech LBI, it can miss some important regions, but it can capture by the empirical Bayesian method. And also we can successfully identify the procedural bias that surrounding the lateral ventricular. And we first review some univariate methods from the hypothesis testing, such as the two-sample t-test, and also the BH procedure. The two-sample t-test is comparison score between two groups, and then it can calculate the p-value under null hypothesis, but it cannot control the FDR. And for the BHP procedure, it first ranked the p-value in ascending order, and it selected the feature that are less than the alpha to the n. But it is too conservative in the feature selection. And the Efron proposed a local FDR, which is a empirical Bayesian method. It is a two-group method that the Z statistics is composed of two groups. The P0 denotes a prior of being null, and if the feature belongs to the null group, it is generated from the its density is f0z, and if it is non-null, the density is f1z, and we can calculate the FDR for each feature and which is the probability for each feature to be null given the statistics C, and we can implement the central matching and also kernel density to respectively estimate the F0Z, P0, and FZ. But the limitation is it doesn't consider the spatial coherence, and the FDR smoothing method consider to model the prior for each voxel and with which introduce another parameter beta, and it tends to solve the negative of the MLE, and also with additional penalty term that which is the fused lasso penalty, and that can consider the prior of spatial coherence. But there are also two limitations, which is the heterogeneous issue, that the procedural bias and the lesion features are heterogeneous because the procedural bias denotes those enlarged features as marked in the blue. They are surroundingly distributed around the lateral ventricular, and also the lesion features are atrophy as marked as the red, and they are more clustered compared to the procedural bias, so they have different degree of spatial coherence. In this regard, we propose to divide the whole graph into three parts. The graph over the procedural bias, and the graph over the lesion features, and the biparate graph over both the procedural bias nodes and the lesion features nodes. And those, because they have different degree of spatial coherence, so they are penalized with different hyperparameters. And because the loss is not convex, we introduce latent variable for the feature to be non-null or null, and we can implement the EM algorithm to solve the latent variable and the parameter beta. And after that, we can calculate the posteriori distribution for each feature to be null, given the estimated feature and the Z statistics. And so with the incorporation of the heterogeneous smoothing, our method can outperform other methods, including the univariate method and multivariate methods, because for the univariate method, they didn't consider the spatial coherence, but for the multivariate method, they can suffer from multicollinearity problem. And this is the result of our feature selection result. We have mentioned it earlier, and we also calculate the stability if we run the 10 cross validation, and the larger value of the MDC, and it means that the feature selection result is more stable, then our method is more stable than others. Okay, so this is the end of this talk. I'm looking forward to your questions. Okay, if there is no question, I will pass the talk to the Professor Yin Tao. I will first introduce the Professor Tao, and Professor Tao Yin received his PhD degree in operations research from Columbia University in 2006. And he was a professor with the Department of Mathematics, University of at the UCLA before joining Alibaba Damo Academy. During 2006 to and to the 2013, he was with Rice University. His research interests include computational optimization and its applications in signal processing, machine learning, and other data science problems. He invented fast algorithms for sparse optimization and large-scale distributed optimization problems. He has won several awards, including the NSF Career Award in 2008, the Alfred Sloan Research Fellowship in 2009, the Morningside Gold Medal in 2016, and the Damo Award and the Ego Ballas Prize in 2021. He has co-authored 7 papers receiving Best Paper Type Awards. He is among the top 1 cited researchers by Collaborate Analytics. So let's welcome the Professor Wotaoyi.
Right. Thank you, Xingwei, for the introduction, and thank you all the audience for coming. And I'm going to talk about learning to optimize, which is an emerging technique that has been developed in different ways over the last decade. And on some of the on some of the applications, learning to optimize has been extremely successful. So because we have limited time, and today we're going to focus on algorithm unrolling, which is one successful form of learning to optimize. So before I start, I want to acknowledge some of my collaborators, and lots of the materials of this slides have been prepared jointly with Jialing Liu also from Alibaba, and Xiaohan Chen from UT Austin. And materials were taken from this A-lister paper as well as hyperlister paper, which is pretty recent. And there have been 2 survey papers. And there's a survey paper we wrote last year called Learning to Optimize, a Primer and a Benchmark, together with all the codes on GitHub. And about 2 years ago, there's a survey by people from UPenn, Penn State, and Israel. It's called Algorithm Unrolling. It's dedicated to this topic. And this talk will include some materials from Algorithm Unrolling, the survey paper, as well as the new development since the survey was written. So let's get started. And I'm gonna first compare machine learning with optimization. So machine learning is some kind of induction. If you think about supervised machine learning, you're given a set of problems as well as their answers, and they're posted as training data. And you train a machine learning model, and after training, the model can give answers in the future. This is called induction or mimicking. Optimization, on the other hand, is more like a prescription. When you give, you're giving optimization, it does not need any training, and you give problems as well as how you would evaluate the answers to the optimization solver. The evaluations can include what means it's feasible, what means it's optimal, or how well the solution is. So you give these to a optimization algorithm or solver, you get the answer, hopefully the best evaluation. This is more like a prescription. Learning to optimize certainly combines machine learning and optimization, and it will get you the better solutions, the solutions with better evaluation, or get the solution much faster, like you're doing machine learning. And in order to achieve this, we use training from machine learning, and we learn from the records of optimization or past replays of optimization. So learning to optimize is a combination of the 2 fields. So let's compare learned or optimization or learning to optimize with classic optimization. There's a stark difference. Classic optimization is usually consists of some kind of analytic algorithm, and they are handcrafted by experts, and they're based upon their experience on theory. For example, Danzig's simplex method for linear programming, or Nesterov's accelerated gradient method for convex optimization. They're both written in like half a page. In case of Nesterov, it can be written in 2 lines as an iteration. And when it comes to solve an optimization problem, the practitioners will often recognize the property or structure of their problem, sometimes involve some kind of a problem reformulation to a standard type. And then they pick the algorithm for the standard type, and that's it. Learning to optimize, because it combines machine learning with optimization, it sort of have the practitioners involved in the loop of designing the process. So what experts do, they propose learning to optimize templates, propose training procedures, and write papers. What practitioners do is, according to their problem structure, they take a template, and I'll be more explicit about what kind of templates we can choose from. And very importantly, they have to collect their own training data, which is a set of optimization problems and their solutions. And then they apply a training procedure. And then this procedure turns a L2O template into an actual algorithm. And then they apply the algorithm to their future problems. And so what will be the advantage of doing this, other than having the practitioners do more? Well, traditional classic optimization problems can have two issues. One, the model might not be the best model. The model might not describe the solution you want, especially, for example, in inverse problems, where my other tutorial speakers have shown the design of the models can be tricky. So if you know the true answers but have hard time getting the right models written, you may use learning to optimize, because it's skip model. It can give you directly an algorithm, and that algorithm can be trained according to the data, according to true solutions you have. The other problem with classic optimization, especially with first order algorithm, is it takes a long time, can take a long time to finish, to converge. Certain first order algorithm easily takes thousands of iterations and can take tens of thousands of iterations, while learning to optimize, as you will see, often take about 20 iterations. It can be 2 order of magnitude acceleration if you go down this route. Okay, so without further ado, let's be a little more concrete. So let's compare learning to optimize with neural networks. So learning to optimize, one approach of learning to optimize is actually based on existing algorithms. Draw a comparison between neural network and an iterative algorithm. Here's an example. Many neural networks can be written as a linear operator applied to the current parameters plus some kind of offset, and then going through a activation function, a nonlinear mapping, like a RALU. Here's an example of a very simple gradient descent iteration with projection for constraint least squares. And the problem is to minimize ax minus b, subject to x stays in a set C. A typical algorithm is to write it down like this: gradient descent and projection. If you look at this, the inside is just a linear operator applied to x, and then there's offset, a constant term, which is a transpose b. And then you do some kind of projection. So it looks very similar. However, there are also differences. In many neural networks, the operators at every layer are different. So these operators vary in k. And usually the total number of layers, not that big. We talk about maybe 10 or 20 or 50, occasionally a few hundreds, but not more than that. However, these kind of iteration can easily run thousands. So the question is how to design neural network, use the freedom that every layer can be different, and then use deep learning techniques to find these operators to improve the optimization performance. So this is what learning to optimize aims to achieve. Okay, so I'm gonna start talking about how these operators are chosen, the different approaches, which is also called neural network architecture design. There are a set of papers that appeared around 2013 through 16 or so, and we call the model-free method. They just essentially take a neural network, a standard neural network, and initialize it and train it on optimization input and optimization output. So it's a 40 data driven, 40 driven by the definition of an optimization problem as well as their solution, and to train end to end to do optimization. Well, there's some benefits, because as I mentioned, usually neural networks have fewer layers than compared to optimization iterations. It takes a lot of time to train because there's usually 40 connected neural networks or some kind of RNN. And optimization, by the way, can be very difficult. So optimization is generalization of least squares. Optimization is generalization of essentially combinatorial problems, because you can have equality and inequality constraints. So optimization is not simple at all, even if you just consider convex optimization. So you train a neural network end to end, like a mapping, to solve a convex optimization problem. It's not easy. So it tends to have a very wide, very dense neural network. Also, the problem is even when you can achieve accuracy on training problems, it's very hard to attain the same kind of accuracy in testing problems. In other words, a poor generalization. Typically in optimization, if you write an algorithm or you write a solver especially, you need to at least guarantee 4 to 6 digits of accuracy. The 3 to 4 digits of accuracy for machine learning problems, and at least 6 digits of accuracy for, say, operations research problems. But these neural networks cannot easily achieve that when you slightly change the problem in test time. So people have turned more to model-based. The model-based method has some kind of a resemblance to existing optimization algorithms. And I'm going to mention 3 type of model-based algorithms: an algorithm unrolling, which is this tutorial is about; plug and play, which is another class of method where you replace a nonlinear operator in the optimization problem by a neural network, but the whole framework is still looks like a traditional iterative algorithm. It's just the one component, or maybe 2, replaced by neural network. And then there's something called deep equilibrium or fixed point network, which basically replace one or 2 layers of a traditional neural network by a fixed point iteration. So this plug and play embed neural network in a classic algorithm, classic optimization algorithm, and this method embed some kind of a classic algorithm into a neural network. And the algorithm unrolling is, I'm gonna spend the next 30 minutes about. And you can look at our survey that compares and defines and compares and explains how these different methods work. So remaining of this tutorial, I'm gonna define algorithm unrolling, give a few examples, and then I'm gonna focus on a specific series of work that called LISTA for sparse coding, for L1 minimization, and explain over the years how this LISTA series of work have evolved from something does not generalize really well or have lots of parameters to train, to something that only has like 3 parameters to train in the end and perform just as well. And then we're going to talk about some theory, and then we draw some conclusions. So what is algorithm unrolling? The 2 steps. So you pick a classic iteration of optimization, and then unfold it, repeat it, just like a neural network. And then importantly, very importantly, you look at the algorithm, look at every step, and you choose to relax a set of like matrices or a parameter or operators into free parameters, and then let these parameters be trained by data. Here's an example. So this is the Lasso model. Previous tutorial speakers must have introduced them pretty well. Just for the sake of completeness, we want to recover the signal, which is encoded by a matrix A, perhaps with noise. So you get B and A. You didn't know the true signal, don't know the noise. And you try to recover it and approximate to X true by solving this optimization problem, where this part pursues sparsity, where this part pursues fitness to the observation. And this can, of course, generalize to many other fields when you replace L1 by other structure-induced regularizers. The simplest algorithm, and we're not talking about linearized Bregman, this is even simpler, is this iterative softness thresholding algorithm. There's a step size alpha that appears in this step as well as that step. So convergence requires a proper or small enough alpha, or you can do line search at every iteration. And this step will reduce the squares, and this operator is called softness thresholding operator will reduce L1. So they alternate between these linear operator and nonlinear operator. Okay. Now let's rewrite this iteration. Introduce is theta equal to lambda alpha, where lambda is the parameter in front of L1, alpha is the step size. We just combine them into one parameter theta. We put it associated with the thresholding operator. And then we just rewrite so A transpose and this operator as matrices W1, W2. We simply write it like this, so it resembles a operator of a neural network. And then instead of fixing theta W1, W2 for every K, we let them vary. We start from K equals 0 all the way to the end. And then we can write this iteration in this particular form. Of course, if we choose W1, W2 and theta like that, then we recover E-style algorithm. But for this new iteration, it resembles so much like the neural network. This is typical way of people writing a flow of the neural network. When we write iterations, we go from right to left. So the operations, is applied from right to left. And when we write neural network, we go from left to right often. So for example, you input X0. X0 going to be multiplied by W2. And B is also input multiplied by W1. And then they are added. And then it goes through together, the sum goes through this nonlinear operator, the thresholding operator, which generates the next iterate. And then you repeat this process. And every block can be different because their parameters can be different. So let's say you fix a K. Let's say fix this big K, and then you train on all these parameters. And when these parameters are trained, the algorithm or the neural network is defined. So this is the idea of Gregor and LeCun from New York University about 10 years ago. So they realized, or they conjectured that if you train this and then you applied it to a set of problems, not all Lasso problems, but a very similar set of problems. In particular, all these problems, all the problems in the set have the same matrix A. The signal can be different, but they also have the same sparsity, if I remember correctly. So they have a same sensing matrix A, different support, different values on those X, and different noise. So they simulate many times of this sensing process, collect the true signal, the results, and then they send it to training. I'm sorry that this thing is a little cut off on the screen. The training aims to find these parameters for all the layers, and they pick a pair of the true signal as well as the noisy compressed descending, and then they compare the output of the case layer, which is the output of the neural network, to the true signal, and the output depends on these parameters over all the layers. Because once you define these, you define the neural network, and this is neural network output. So you find the parameters such that the case layer output is close to the training signal. And you do this for a set of signals. Okay, and then to their surprise and to everybody's surprise, the result is extremely good. So after the neural network is only trained for 16 layers, it's okay equal to 16, and you apply this neural network to test the problems that are similar. They have the same A, but different sparse signals. And then you realize, this the performance is much better than the ISTA algorithm corresponding to different lambda. So first, let me say something about lambda. Lambda is the L1 penalty. So this larger lambda imposes more sparsity. So signals result will be sparse, but they're going to be more biased. So so bigger lambda also means actually faster convergence, because you very quickly get sparse solutions. And smaller lambda, less sparse, less bias, but take longer to converge. And it takes usually a couple of hundred iterations for ISTA to converge, even on a simple problem. However, they take about 16 iterations to converge to something better. They do not really solve the lasso problem. However, their algorithm is trained. So their algorithm use a lasso's algorithm as a template, and it's trained to try to catch the true signal. So they have better denoising effect, less bias, and converge faster. So this surprised lots of people. So and over the last decades, there have been many papers, like hundreds of papers, that extend this result. And they also have been applied beyond sparse coding, beyond lasso, to image denoising, all these image processing technique applications, medical imaging, remote sensing, as well as other signal processing applications. They also have been expanded to, people start to unroll other popular algorithms like ADMM or primal dual hybrid gradient and beyond. Let me quickly show you some applications. And this is the application of a high resolution image super resolution. That is to generate a high resolution image from a low resolution image. And roughly speaking, what they do is they break an image into small patches and try to find similarity among those smaller patches. And then essentially the high resolution information is borrowed from other patches. And this can be formulated as an optimization problem. And there has been classic method based on total variation, neural network-based algorithm, which needs lots of training, and unrolling-based method, which needs less training and more. By the way, unrolling algorithm is more interpretable, because you can roughly understand what these iterations are doing. And then this unrolling results is the best. And another application is CT reconstruction. And this is the phantom image, and there are more real images out there. And we try to recover this image from their line integrals. And this is classic total variation results, CNN result, and this is unrolling results of newer. And from the same number of measurements and noise, unrolling results is the best. And another application, image blurring. Here, the image, true image is X, and assume there's a blurring kernel that does sort of a local averaging onto the image, and then corrupted image is corrupted by some noise, and you need to recover, in some cases recover X from B and K. In some other cases, you only given B and you need to recover K and X. That is called blind deblurring. Here are some results, and this is total variation results and some distortion. They're very sharp, but they're actually not authentic. There's some kind of smearing going around. This is CNN, convolutional neural network results. It does a good job, but not clear enough. You lost some kind of sharpness. And this is on rolling results, pretty recent, which is much better. Okay, well, let me turn to the methodology itself. There are some challenges we have to address before we can really make it work, make it to the practice. Basically, 3 challenges. So one, there's really too many parameters to train if you just unroll it and let everything be free. Suppose the A matrix in lasso is m by n. So the signal had n dimensions, you take m samples, and then you unroll it to k layers, and you have to train these many parameters. Now, it may not look large, but the larger this number, the more difficult the training is. And it also makes it more difficult to generalize. In particular, this K thing can cause trouble. Gregor and Kuhn only trained for 16-layer neural network for a reason, because so optimization, when we think about optimization, the iteration, you keep apply same operator to the output of the previous layer, and so later layers aren't really sure what previous layers will generate. This is very different from image recognition. So image recognition is, roughly speaking, the previous layers are feature extraction, kind of transform an image into a form where they start to people can't really understand what's in the middle, but they start to become in a form that later like a template matching layers can start to differentiate these images. So more like a feature extraction at the beginning and at different scales, and then feature template matching at later layers. So classification roughly works like that. But optimization is actually a more difficult problem than classification. The later layers have to sort of be trained after the previous layers are already trained. So later layers see what the previous layers can generate, and then try to make the solution a little better, layer by layer. So in order to train, let's say, if you set K to like 50, you're going to be already very challenging. You sort of have to train the first layer, and then train the second layer together with the first layer, let them all vary, and then let these 2 layers train to some kind of convergence, and then you train the first 3 layers together. So this training process is not just like a grow linear with K. It grow at least quadratic, even cubic with K. So a large K can cause difficulty. And you don't really know what K you should choose, because when you change M and N, or when you have slightly less sparse signal, then K have to increase. So K vary from application to application. So choosing K can also be an issue. So this is the first problem. Second challenge is interpretation. Optimization would traditionally apply to very critical areas like medical imaging, where doctors will make decisions based on the image, and on operations decisions like setting prices, setting inventory levels. If you want to now train it, And because these decisions are very important to practitioners, you will have to sort of explain what's going on and roughly what these algorithms do. And being able to interpret or explain what the algorithm do is also related to generalization performance. In other words, whether these algorithms can be dependable on in practice when these algorithms apply to data it has not really seen before. So generalization performance typically it's when the algorithm is more explainable, it tends to be more reliable. It tends to generalize better, and which is also the case in L2O. So in the story I'm going to show you on Lista, you're going to see as the years progress, the algorithm become more and more reliable, and it can generalize to now finally can generalize to like an A matrix you have not really seen before, or the noise level that has changed from testing to training. But finally, when you apply the algorithm totally to out of distribution, never seen before, signals that not like training at all, you need some kind of safeguard. So the algorithm can perform just as well as the classic algorithms. Okay, so over the past few years, this has been addressed for Lista. This is good news. Let me show you. The first step people do is to simplify, to reduce the parameters. So they make this observation. Suppose there's no noise. Suppose there's no noise, and you want the output to converge as the layer increase. You want the output to convert to the true signal. Then through very simple calculation, you see that theta have to converge to 0, and this quantity have to converge to identity. In other words, on W2K, asymptotic must equal to identity minus this matrix. And then you take out Greg and LeCun. You repeat the algorithm and plot these values. You realize they are the case. All right. So analysis, because optimization, you can write down the formula. You can differentiate the formula, which is a blessing. It's indeed the case. Now, this has motivated people to just simplify the network by tying these two together. They say, I just need to learn W1K. And once I learn that, I simply write W2K like this. I just let it net this equal for all K, which roughly eliminates a little more than half of the parameters because this matrix is bigger. This matrix is a little smaller. Okay, so once you do this, the neural network now look like this. You need to learn this matrix, which is multiplied to the residual, and you need to learn how to threshold. And we call it weight coupling or CP. Well, this reduced parameters from that many to this many. You get rid of n squared k, where n squared is the size of W2. Because n is often greater than m, can be like a double n, it can also be a few times of m. So this can often lead to significant reduction of parameters. And interesting to observe, once you do training, this reduction also makes training more stable. The training gonna converge faster. Okay, this is first technique. Well, the second technique is called support selection, which has happened in a few papers in compressive sensing. And what does that do? It selects a subset of components, usually the largest components during the iteration, and let them skip them on software thresholding. So they are bypassed. Okay, if all the selected components are the true non-zeros in the end, then skipping this software thresholding or bypassing software thresholding will reduce the bias that software thresholding introduces. Now, how do you select them? Well, you have to select. You don't really know. You don't really know where to cut it off. So we do it by fraction, and this fraction depends on the iteration, and this fraction is also a trainable parameter. You can tune it by hand. You can train it in data. Now we have 4 algorithms. We have LeCun and Gregor and LeCun. 10 years ago, we have Lista with the weight coupling alone, Lista with the support selection alone, and the Lista with both techniques together. And these are more like 5 years old. So 10 years old versus 5 years old. Let's do some kind of a comparison using normalized mean square error. And we generate test signals. We use 50 sparsity, half of the samples compared to the signal dimension. And then the Gaussian entries of the A and magnitude of signal also sample from standard Gaussian. Okay, so you see something like this. The horizontal axis is the iteration or number of layers. Y-axis is the dB, the log scale of the error. These two curves corresponding to traditional algorithms. One is standard and the other is Nesterov accelerated. And they take hundreds of iterations. So if you plot up to 16, they don't really show any promising results. And these are the learned algorithms. And weight coupling is the purple one. Without weight coupling is the green one. So no weight coupling, and this is the 10-year-old, this is a 5-year-old. And there's something called learned approximate message passing, which is like a similar line of work, similar like a parallel line of work. And then let's do support selection. Once you do support selection, the error further drops. If you combine them both, with coupling with support selection, not only do you have fewer parameters to train, you have better results. You converge faster, come to something that's much more accurate. This is noiseless case. You haven't applied any noise during the sensing. If you apply 30 dB of noise to the same thing, you won't be able to really do much better than the 30 dB at the results. But the relative positions is still, the more reduction you do, more like a coupling and support selection you do, the better the results. Okay, that's far from the end of the story. People, actually we, started to further analyze the optimization. So what we can do. So inspired by an analysis, around that time, I start to think about how can we prove things? How can we show some kind of a generalization performance, show that learned algorithm has convergence guarantees. And inspired by this analysis, we just start to think, well, let W vary at every iteration does not really seem to help the theory. This freedom is something maybe we don't need. So we just test tying all the WKs for all K together. Which is funny in the sense that we started making a neural network, we relax everything, we unfold and relax, and now we reverse the process and make all the W the same W for all iterations. So you do that, well, of course, you significantly reduce the parameters. The longer one W for every layer, you have only one W for all layers, and then this K corresponds to the threshold, because it turns out threshold is important. Threshold is more important than that W. Okay, and then we did the training. This is Lista. I don't know why I lost so many letters, but this Lista, CPSS, this is TI, Lista. And it turns out they have similar performance. And TI Lista, because they have fewer parameters, is a little easier to train, they perform even better. Okay, so great. We now know W doesn't have to change. But what W needs to be? So we further go down the analysis, and then borrow from classic comparative sensing analysis. There are like a few lines of work that use different conditions. One use RIP, restrict isometry property, and the other line, main line, use coherence. Coherence, or called mutual coherence of A matrix, is defined as the inner product, size of inner product between different columns, assuming each column is normalized. So which is basically the max cross correlations between pairs of columns. You can also define mutual coherence between two matrices. By the way, when mutual coherence is small, you have better sparse signal recovery. So assume that one matrix has normalized column, and you look at this number. By the way, I does not need to be different from J. You can use I different from J if Wi transpose AI equals identity. Okay, so to normalize the same pairs, and then when you measure the cross pair inner product. So it turns out this mutual coherence between two different matrices will also help recovery. So we turn to TILISTA. We look at TILISTA, and I also lost this character. We look at the mutual coherence. We plot the mutual coherence as training progress. This is training, like a training time. To the right, you train for longer time. And you observe that this W, the mutual coherence keeps coming down. And then we start saying, hey, maybe we don't need to train W. We can set W according to mutual coherence. And that's what we did in a paper that was like 2 years old. It's called Analytic List, which gets fabulous, like a second best review scores of ICLR of that year, with a couple of tens and some lines. So I'll tell you what A-lista is, but this is the W that A-lista generates using an optimization problem without training. Okay, so we use this principle, use this observation to design W. And we design W to minimize, to let the columns normalize and minimize the Frobenius norm squared. We did not use the definition of mutual coherence because it's a difficult optimization problem to solve. We do an approximate. We just simply solve a quadratic program, which is much easier, which essentially boils down to taking some kind of matrix inverses. And when we call the result W tilde, with W tilde fixed, we now learn the step size and threshold parameters. So this reduces the free parameters to about 2K. And the training now takes only minutes on a standard graphic card. And then we did the test. We find, well, this A-lista with only 2K parameters to train performed just as well as previous methods. Sometimes a little worse, sometimes a little better. So if you compare, this sequence of work from 10-year-old, about 5 years old, about 3 years, about 2 years old, you reduce the parameters, you reduce the training time from hours to minutes, and you get similar performance after this this first step. Now this is a little worse because they simply have too many parameters to train. It has the potential, but training cannot reach the potential. But all the other, because of the simplification, it has reached the potential. Okay, and then we start to think about how to make it better. One thing that has bothered us is we have to train like one set of parameters for every A. Well, this can be practical in some situations where you do MRI or do CT, or you have equipment taking measurements. That equipment defines A, so that A is stable. But there are other situations where A can vary like crazy. For example, sparse coding, or you do some kind of gene analysis, want to find out the genes responsible for certain diseases or genes that are responsible to certain drug treatment. So we start to think about how to make the method reliable to A. The first step we take is to perturb this matrix A. So the measurement, this compressive sensing measurement, is a perturbed version of A. We're given the perturbed matrix, given y tilde, we try to recover x. So now you must handle basically varying A. Well, remember, when you have an A, you're going to have a W by solving this quadratic program that approximately reduces the mutual coherence. But that itself is an optimization problem. So why not using a neural network to do that optimization approximately? So we introduced the second neural network to generate W from A. And then the method takes 3 steps. So we have to train this neural network, which we call encoder, that generates W from A, given a set of training data that were lots of pair of A tilde and W tilde. With that W tilde and A tilde, we take compressive sensing and try to train an A-list network so we can recover good signal X. And we train them in sequence and finally join train them together. So, and this becomes the process. Once this jointly trained, this 2 networks is jointly trained, what it can take is get A tilde, get Y tilde, it will automatically generate W. And it'll automatically plug into A-list and get X. Okay. And we created some kind of a test of robustness, and indeed it's more robust. And I will not, because of time, I'm gonna skip the details of this test. Trust me, it's more robust. And then there has been even more results, which is more excellent in recent years. This has become like 1 year old. So these people, I think from Michael Elat's group, and they came and they look at our A lister, and then they say, hey, how about make this W have certain form? Instead of training W, we train A transpose U. So we train U, not A, right? We train U. U is symmetric. Now, the benefit of this is once you do this iteration start to have a Diaplov function because of the symmetric positive definiteness. Once it has a Diaplov function, training becomes more stable. And in addition, you can now train without knowing the ground truth. You don't have to, like during training, you don't have to use a traditional solver to solve for the accurate solution or use the true signal to train. You can just train according to the Diaplov function. Okay. They also add a momentum, so they add a little extra term on there, and they show better results. Okay, so look at this paper; it's very good. And then those are the development. But for the moment, let me switch to theory temporarily. So A-lister and Ada-lister and some other paper also start to get good theoretical results. A-lister shows that given low mutual coherence and for any sparse signal, significant signal X, there exists parameters you can hand choose such that A-lister converge linearly. Okay, so it only shows existence, while it does actually construct it. However, this handcrafted parameters that shows linear convergence is not as good as the trained parameters. So it tells you that there's a capacity there, you can do linear convergence, which traditional ESTA algorithm does not have. So traditional ESTA algorithm have a sublinear phase and then a linear phase, but learned ESTA can converge linearly from step 1. So Ada-lister shows that linear convergence can be achieved robust to dictionary perturbations. And the step-lister, there's some kind of necessary conditions. And then the people who analyze the Rademacher complexities of lister network. This is the concept from deep learning. And then interestingly, we show the lower bound. We show linear convergence is the best you can do under some setting. You cannot do better than linear convergence. So train any W, and even you can let W vary across iterations. Train any W. And then you consider the set of a sparse X with uniform random supports. You don't know its support, but the sparse support and uniform random values. And then with high probability, in other words, for for almost all these sparse X, linear convergence is the best you can get. You cannot get superlinear convergence. So we saw it was down and it was not down. So last year, we realized you can actually get superlinear kind of convergence by relaxing things. There are two things that are important to get this superlinear behavior. So first, you have to definitely let a selected number of largest entries bypass soft thresholding. And this bypass number, how many of them bypass, have to be adaptive to the problem at hand. And then we come up with analytic formulas to choose the thresholds. Remember, W is already analytic. The step size, the thresholds, as well as how many entries you're going to bypass are still varying. And we come up with analytic formulas which has like 3 hyperparameters, and you can just grid search those hyperparameters. Now, what these analytic formulas do is they are going to adapt to each instance. They're not trained for like a set of signal. And they become analytic, so they can be basically adapt to each instance. And then we theoretically shows that there exist the parameters hand chosen to obtain superlinear-like error reduction. When I say superlinear-like, I didn't use the word superlinear because superlinear is a asymptotic concept. And here, however, we only take, like, say, 20 iterations. So we want the error going to decay quicker and quicker. So that's like superlinear-like. So these are the formulas. I'm not going to explain why they are such, but these formulas are computable. They only depend on the parameters at hand, all the known information when you carry out the iterations, and the formulas are motivated by analysis. We were thinking, we were trying, recently trying to symbolic search, see whether similar formula can come out of data without human intervention. So this reduces the parameter from k to 3, and once it's 3, just do a grid search. And this is a result of hyperlista, which is surprisingly good. On the same set of data, it's fast and robust. On the same set of data, is even better than A-lista, and some improved version of A-lista motivated by ADA-lista. And we start to change. We start to vary the sparsity level. We start to there's some cutoff here. We start to vary noise, start to also vary some kind of a setting matrix. So you see, this thing's much better because it turns out more analytic the formula is. When it performs so well on the training data, it tends to generalize better, at least in some directions. Because of time, I'll just stop here and I'll list some uncovered topics, which may perhaps are good for design some future tutorials. And there are topics that are on the extend sparse coding to matrix factorization and do iterative hard thresholding rather than soft. Improving lista using some better threshold, gated mechanism, etc. And pay attention to something like this. This one came out of a group, and this tells you how to add a safeguard layer. So lista gonna have a guaranteed performance compared to convex optimization algorithms. And this work allows K be a finite, large, go all the way to infinity. So when K is infinity, the lista cannot be trained. It's gonna have to be something else. It's called deep equilibrium, more recent work, and fixed point network. And then Rebecca Witt's group have demonstrated better image recovery results using this new technique compared to lista. So let me summarize. We see a huge room for optimization speed and quality to improve, and seems integrating machine learning, integrating that with machine learning is a viable approach. And you think about algorithm unrolling, it's integrated data-driven, which is slow at training, fast at testing, and a data adaptive with analytic algorithm. Analytic algorithm is fast It doesn't need any training, maybe tune a few parameters at most, and then can be slow at practice, but it works with universally for a set of problems. You can combine the two to create fast training, fast real time, and algorithm adapted to the data. So it will do better and when they see the similar data. So despite all the success in sparse coding with the theory, with the reduction in parameters, with better generalization, the same has not been said, has not been applied to other algorithms, so other applications beyond sparse coding. On imaging, more needs to be known. On signal processing, more needs to be known. So far, the success is only limited to sparse coding. So I would invite the audience to look at this and perhaps work on this area. And finally, a list of set of references that I covered in this lecture. Okay, so I stop here and I wonder if there are any questions from the audience.
Hi, Professor Wotao. Well, very interesting talk, and I have a question that if the this algorithm unrolling can be applied to if they can be applied to generate a regularization solution path rather than just the optimization the convergence analysis.
Okay, I think it can. It just has not the frontier has not been advanced to that point yet. I don't see any like obvious obstacles from like going from generating one signal to a whole path. Perhaps the people have not pursued that because here people have been pursuing speed, right? When you generate an optimization path, it's sort of you did algorithm. You did essentially like generate optimization path by an algorithm. You run an algorithm, as the algorithm run, you get a path, which is good. Perhaps people here has been pursuing just generate one good solution fast, so they have not thought about that.
Okay, I see. Thank you.
So an obvious question is, can you do this onto say linearized fragment, right?
Yes, yes.
I can tell you that some people have tried. It has partial success. It is not as easy to unroll ISTA, unroll linearized fragment, unroll any dual algorithms, because people haven't really understand or maybe have not found the right training method. So ISTA is not a fast algorithm for lasso. Some dual algorithms like ADMM or primal dual algorithms are faster. And interestingly, I think training a unrolled ADMM using just the just to catch the primal solution is not a good idea. You probably need to catch both primal and dual solution.
Oh, okay. Okay, thank you.
Very good question. Okay, so if there's no more question, I guess we're gonna stop here. And I wonder if the an organizer want to say something.
Yeah. Thanks for the great talk. I think it's almost time, and it should be the end of this tutorial. Any comments from Professor Yuan and Xinwei? Do you any words want to say?
And I'm curious about what's the opinion of Professor Yuan Yao's about the solution path if we use the algorithm unrolling.
Yeah, I guess we need to discuss about that later.
Okay.
Yeah. maybe Watao can.
Yeah, one thing is, I was thinking about this as you were speaking. How do we define the quality of solution pass?
Yeah.
Right.
One motivation is we always in linearized Bregman, we always use the same step size. And when we do the deep learning sparsity, because different layer are kind of different scale. So keep same step size very time consuming.
Mm-hmm.
With a lot of computation. Some layer may be explored very fast, some are very low. I think Yanwei's student Liu Chen, when he explored sparsity for deep multi-layer neural network using LBI, suffered that issue. So he manually tuned the step size, somehow make the layer more balanced. I think that somehow says if we can know the order, which feature appear or which variable appeared first or earlier than another, if the order we can know, then we have a good quality for the regularization path already.
Order which?
The order of the variables appear on the path to be non-zero on the path.
I see.
Yeah, that might be something, yeah, like AUC curve or something. I don't know. Yeah, we don't care too much about the magnitude in the past.
But it's like which come up first.
Yeah, but which come up first in this sense is more important.
I see.
Yeah.
Good point.
Yeah, that's an interesting question. Lots of thought-provoking results. How about for matrix or tensor? Single value thresholding is also very expensive.
Right. There has been great results on matrix low rank factorization, stuff like that.
I see.
Yeah.
Okay. Yeah.
All right. Great.
Yeah.
So if there's no more question from audience.
Yeah, I guess it's good to mention that we have a website on this tutorial, and all the speakers will have uploaded all the slides there. And so, in case we can also post our contacts if any audience, want to contact us more about these stuff, and they're welcome to do by email.
Yeah. Yeah, we will. Well, we record the whole process of the tutorial, and we will release the video on the website. And just in case the audience are interested in some part of our talk.
Okay.
Yeah. And thanks all speaker, and thanks all audience. And this is end of this tutorial.
Yeah. Okay. Thank you all for coming.
Thank you.
Yeah. Okay.
Bye.
Good day or good night.